the research I normally do is stuff I do with Manuel, lots of equations, etc. But I figured for the 3 hours I have here, I try something different, which is to, as Manuel said, summarize 600 pages into 3 hours. So obviously this means we cannot go into any detail. I aim at giving you a good idea of what the second law describes, why we need it, and how we use it. In particular in problems, in applied problems, like what I put in here, the jet engine. So there's a lot of stuff that you see in your daily life that has to do with the second law. And I also will try a little bit to give you an idea of why we observe what the second law describes. But that will come in the second half of the presentation, or this last third rather. Before, we just find the law, use it, and you will see that it is everywhere. Well, probably you know some of it. It's even better. Of course, to make this a successful presentation, I need your help by asking whatever question you have on the fly. We can always interrupt, we can clarify things. I mean, I summarized a lot of stuff into this, so for me, I might have forgotten some things that are important for the background, so don't hesitate to ask, okay? So, the second law and all its consequences, or not all, but quite a number of them. So let me see that this works. There we go. So what do we do if we develop the science? We observe things going on around us. We try to generalize the observations. We formulate some laws and words as equations. Then we use those laws to first test whether they actually describe what we observed, and then to make predictions for other stuff that should follow the same law. And then, if we can, we try to understand the laws. And so this is pretty much the idea of, or the outline of the presentation. And we start with a very simple observation. And we go to our coffee in the morning, which is very important. So there's this fresh cup of coffee on our kitchen table, and we forget about the coffee. Can't happen in my home, not with me, not with my wife. But what happens to that hot coffee in the cold kitchen when it stands there? No one dares to. You probably have never experienced this. You're coffee addicted. Okay, so we all know, after a while the coffee will be cold. And pretty much it will have the temperature of the kitchen, which I call TK here. We could argue about that when we talk about the first law, so there probably will be a small increase in the temperature of the room, but essentially the coffee will cool down to the kitchen temperature. So this is equilibration of temperature. And you would never see, so there's an arrow here, right? And the arrow goes in only one direction. It goes from left to right, from hot to cold. The coffee will cool down. You will never observe the opposite, where you wait in the kitchen for your cold coffee to get hot again, right? You know that quite well. So there's a direction in this process. Okay? I drink my coffee with milk. And so I take my milk and I pour it into the coffee. And I wait a second or two or three. And what will I have? I will not even dare to ask you, a complete mixture of coffee and milk. Always makes me mad. I go to a coffee shop, Starbucks, lots of Starbucks in Canada, of course. So you go and you see these people, they pour a little bit of milk in, and then they take a wooden thingy and stir their coffee and throw it out. No need for that, right? How many trees are cut down because people don't understand that the milk will mix with the coffee by itself? I don't know. Quite a lot. Too many. I trust the second law. I just pour the milk, I wait a bit, and I drink my coffee. So, and again, we have this arrow, right? We go from unmixed to mixed state, And we will never observe the separation of the milk coffee into milk and coffee. I mean, you wait, you forget your coffee for a couple of days, there is some separation, some layers forming. That's a different kind of thing. Well, now if you put sugar in, you want to stir the coffee just to make it faster. You can wait for the sugar to dissolve and diffuse also the coffee. But with sugar, you certainly want to stir the coffee, and then you take the spoon out. And after you take the spoon out, what will happen? Your coffee will swirl a while and then will come to rest, right? So it's another process going only one way. So the coffee will move for a while, but then it will come to rest. So it's 3 coffee examples for different processes: equilibration of temperature, spontaneous mixing, and how can we say, destruction of kinetic energy, maybe. Okay, so this is the second law at work, and the first law. So now we want to generalize these experiences into some kind of law, so we need some language, right? The first thing always is you have to come up with some language. So we define a system as any well-defined subset of the universe, for instance, your cup, right, where you pour the milk in, or where you stir, or the kitchen, where you have the cup and the table and everything. And then we have a process, which is the change of any one or more properties in a system, like temperature, pressures, velocities, densities, whatever, mixing state, concentrations, typically triggered by some manipulation of the system, right? So you do something, you pour milk, you stir the coffee, and then with that you have started a process. And what we have just seen in these 3 examples, it's what we can call the approach to equilibrium, which is that after all manipulation stops, we don't do anything anymore. We pour the coffee, we put it on the table. We put the milk in, we don't do anything, we just let it sit. We stirred it and we walk away. So after that, after all manipulation stops, the process continues for a while, but then after that while, the system assumes a unique and stable equilibrium state. So stable means it will not go away from that state unless you do something again, which is a new manipulation, which is you start a new process. And that it is unique is essentially something you have to observe, right? But let's look at the milk and coffee. It will always be the same mixing state, which is the milk is distributed all over the coffee. The coffee that you stirred, it will always be at rest, right? So that is unique. And this is what the second law describes. The second law describes that approach to equilibrium of any system. And this is something you observe elsewhere, right? So you go through life, you look around, and you will always see these processes where the system tries to go towards that equilibrium. So the conservation laws alone are not enough, right? So you know energy is conserved. We will come back to the first law, the energy conservation law, in a bit. But the first law does not forbid at all that you have your cold coffee being hot again or spin faster, right? You stirred it, it starts to spin faster and getting colder. The first law is fine with that. It's the second law that gives the direction and tells you the coffee will get slow, right? And so we need even more language. So now we have system, we have a process, we talk about manipulation. And now we do stuff that the people who know thermodynamics probably have seen. So we talk a bit more about processes in equilibrium. So an equilibrium is a state that you reach after all that manipulation has stopped. So when you now imagine a very, very slow change of property, and not every kind of change will work. You cannot stir slowly enough to make a quasi-equilibrium process. But maybe you can heat very, very slowly, or compress very, very slowly. So if you start in an equilibrium and you make a very small change, you will be in an equilibrium state right away after that change. So it's not that after your manipulation, which is a little squeeze, say, on the system, is over, that something will go on. You just, if you squeeze very carefully, very little, and you do that in many steps, so that after a while, if you do it very slowly, you have macroscopic change. So if you can do that, then you are in equilibria of your system all the time. So it's very difficult to do. In practice, you probably will never be able to do it, in fact. Right? But you can think about doing things very slowly, and then you run through equilibrium states one after the other. And this is what we call a quasi-equilibrium process or a reversible process. We need that language in between, so we have to get an idea. And we can formalize the definition of reversible. The easy definition is this. If you see a movie of the process and you run it backwards and forwards and backwards, you can't distinguish whether it's run backwards or forward. Right? So you squeeze very little or you let go a little bit. So you have a system, just these typical thermodynamicists love this piston system, cylinder and a piston. So you squeeze a little bit, you let go a little bit. Can you distinguish whether you see the movie forward or backward? No. A fast process, an irreversible process, is one where you can distinguish between forward and backward. You stir your coffee, it slows down. You see a movie of coffee at rest starting to spin, you know, you see this movie backwards, so this is something that is never observed. So this is the easy definition of irreversible, right? And so in a fast process, the system typically is inhomogeneous process, states. The temperature in the system is different at all points. Maybe the concentration of the milk is different at different points within the cup. And then the process continues until the equilibrium state, where the coffee overall has the same temperature, the milk is equally distributed. And you have no control at all about that approach to equilibrium. You have done your deed, you stirred the coffee, you let go, and what happens after, you have no control. If you have a quasi-equilibrium process, a very slow process, you control at all times what is going on in your system. So there's a difference between control and non-control. Down here I have another process where you distinguish between the possible and the impossible. You put a weight on the axis of a propeller and you let the weight go down in the gravitational field. The weight goes down, the propeller spins, setting in motion whatever you have in the system. And that is something you are familiar with. But you will never see that you have a system, just a container, a cup of coffee with a propeller in, and suddenly the propeller will start to spin and move the weight up. Right? So there are a lot of these processes, and pretty much all real-life processes, anything that you really see in life, has some degree of irreversibility. So the reversible process is something we assume so that we can distinguish very clearly between the reversible and the irreversible. Okay. So here's a more exact definition for irreversibility. That is, a reversible process is a process that can be inverted so that the system returns to its initial state and no changes remain. So this is the definition without movies, which is a bit more difficult to grasp because it's not that easy to see under which circumstances you can or cannot bring a system back to its original state. And irreversible is if changes remain. So we probably leave it at this. I think the movie definition is what we need for our present day. And again, the statement, all real-life processes, everything we really see is irreversible. Okay. So now, it's all words. So we have to formalize, and we have to go and see and get started somewhere. And I like to get started with what I call the closed system, which is, as I said, thermodynamicists love piston cylinder systems. So we have a piston, we have a cylinder around it, and something in there. I should have put M there for mass. A gas, a liquid, a couple of stones, whatever we do, we have something in the system. And now we ask, what can we do to change the state of the stuff inside the system from the outside? What manipulations can we do? And I put all possible manipulations in the picture already, so we can move the piston up and down. We can stir the stuff with a propeller or a spoon, and these coils here, they point towards an exchange of heat, cooling or heating the material in the system. Right? This is what we can do. We distinguish between piston and propeller work. We can do heat exchange, and that's it. And if you think about it, you will not come up with anything else you can really do to the system. Right? Some people suggest microwaves, so you can send in waves which get absorbed, or you have emission of waves, radiation. But all that goes into the heat exchange. Right? So there's little left, nothing left, absolutely nothing left you can do. This is all we can do. Okay? So, I squeezed the zeroth law in between here. So we have defined a system. So for the when we talk closed systems, probably the system would be this: two bodies at different temperatures. We bring them into contact. They can exchange heat, and after some time, we find they have the same temperature. Oh, this looks ugly. They have the same temperature. We know that. That's daily experience. We started with that. That is a coffee example. But this defines temperature, this zeroth law is introduced into thermodynamics to define temperature as something you can actually measure. If one of the bodies, body B, say, is your thermometer, you bring it in contact with body A. Body A is much bigger. The thermometer is very small, so that it does not contribute to the final temperature, really. You wait some time. You know they both have the same temperature. You can understand, you have a relation for the temperature in your thermometer, and you can conclude on the temperature of the other body. Right? So this is the equilibration process again. It's just, for proper bookkeeping, we have to state the zeroth law. So we can measure temperature. Okay? But now, before we go to the second law, we need the first law. We need to stay in order. And here's again our system, and here's a law of conservation of energy. Energy cannot be produced, cannot be destroyed, it can only be moved, transferred, or converted from one form to another. No energy forms listed here yet, that's the next slide, but here is how energy can be moved. It can be moved in terms of heat. We will define heat in a little bit. So heat is exchange of energy because there's a temperature difference, say, between this heating coil and this substance in the system. And it can be exchanged by means of work. And work is force times the displacement of the point of its application. That is what work is, right? So obviously you need a force to move the piston. You will need some force, some torque to move the propeller. So these two things that you can do to the system are related to work. Right? And so the power is, I put dots on here, the dots. Power is work per unit time, right? So work done per time, and heat rate is heat done per time, right? Kilowatts instead of joules. And how do you know the first law? So that's the same thing. Observation, extrapolation from mechanics. People knew there's something like gravity, there is something like kinetic energy. And then very, 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 very careful experiments. I showed you the cup of coffee in your kitchen. You can observe the second law readily everywhere. You cannot observe the first law unless you are really, really careful about your measurement. Okay? So the first law is more difficult to get an idea of than the second law, I find. So what kinds of energy do we know? We know kinetic energy. Let's look at some body, substance, fluid. We put it into little cells, little volume elements in the continuum hypothesis. And we know each cell has a temperature, has a density, has a velocity. So if we sum up the velocity squared in all these cells weighted with the mass of the cell. Rho is the mass density, rho dV is the mass in the cell. So this is just the kinetic energy as you know it from mechanics. I will assume you know this. We sum it up over the whole range of the system, and there is kinetic energy in the system just because there is motion inside. There is potential energy in the gravitational field. G is the gravity's acceleration, Z is the height about normal level, and rho dV again is the mass. And there is internal energy, and this was a difficult step of finding the first law, is to introduce internal energy, which measures something that is inside the substance, inside somehow, and so you could call it thermal energy as well. This is the microscopic motion of the particles, right? So you have atoms, you are in a gas, say the particles fly around, each particle has thermal kinetic energy as well. So we sum up all these energies and we get the overall energy. No temperature here, right? I just made a point, you can measure temperature. You cannot measure energy. There's no way you can measure energy. So energy shows up in the first law, but you cannot measure it. So you have to relate it to something you can measure, and for this we have equations of state, caloric equation of state, which relates energy to density and temperature. These are things that you can actually measure. And also we can relate the pressure to density and temperature by what we call the thermal equation of state. Very simple examples will come. Okay? So we split our energy into all these contributions, and then we know, we have it here. The total change of energy, the total energy in the system can only change by exchange of heat and work. And even if the energy is constant, the total energy is constant, you can of course convert kinetic and potential into internal energy, for instance. Or maybe vice versa. Okay. Simple equations of state, just so that we have something to work with. The ideal gas pressure is density times gas constant times temperature. The internal energy is the specific heat times the temperature. No, not even a dependence on density. Even simpler incompressible substances, the volume, or the volume, specific volume here is the inverse density. Constant density will never change. You cannot squeeze it or expand it. And the energy is a function of temperature as well. So very simple stuff for our examples. Okay? Energy is conserved, but as I said before, the first law cannot tell you that you cannot go on in some directions, that you cannot cool a system, right? So you would take your cup of coffee, it sits there, it will cool down and start to spin and spin faster and faster by cooling down. As long as the energy is conserved in that, you're fine for the first law, but not for the second. Here a bit about work. The moving boundary work, also something we need, right? So work is force times displacement. If you think about it, the cross-section of your piston times the pressure is the total force on the piston, and then you multiply with the distance ds you move. So cross-section times ds is the change of volume. So the power of that displacement is pressure times the rate of change of volume. That is the moving boundary work. We will need that too, hence I had to include it. But here's the important thing about power. There is no restriction on transmission, right? You can transmit power in every direction you like if you just take proper gears and levers, right? So you know that you all run on bicycles, right? So you can have a very low force to climb up a steep hill, for instance, right? You just use levers. You can use a very small force to compress a gas easily if you just take a long lever, right? So there's no direction, natural direction for work. You can just transmit it. No problem. Heat, however, is different. Heat is the transfer of energy due to difference in energy, so in temperature, so very little on this slide. We just call the heat exchange over the duration of the process Q12. We call the heating rate Q dot. Q12 is the time integral of the rate. And here's the important thing. Heat will go from hot to cold by itself, but not vice versa. This is what we observe, right? The coffee will assume the temperature of the kitchen, but you will never go away from that. There's a direction. That's a difference. There's a difference between work and heat. Heat has a preferred path. System left to itself, heat will always go from hot to cold. Work, it depends on what you do. Okay? No direction. And now we can start. With all this before us, we can write down the second law. We just put it in words before. And system left to itself approaches a unique equilibrium state. So let's start with an isolated system. We do nothing to the system. We just have it just sitting there. The system is left to itself and evolves into only one direction towards its equilibrium state. We understand from observation. It will not go by itself away from that equilibrium state. Well, how do we describe this? And this is probably what makes most people nervous about the second law, is that it's typically written as an inequality. Right? Not an equality. We are used to equality. The first law, the conservation of energy, is an equality, an equation. Things are equal right and left, and we are happy. We understand that. We know that from balancing our bank accounts. This is good. But here there is an inequality. There is a sign in the equation which we have to clear. So what do we do here? We just ad hoc try to find an equation which describes this behavior without being able to assign much to the elements of it for now. Right? So we say, okay, if there is only one direction for the system, isolated system, to evolve, maybe there's a property of the system which we call S, and we give it a name entropy, that actually describes that evolution into one direction. And to have it into one direction only, we need an inequality so that we can say, okay, the system, isolated, we do nothing, has this quantity, this property, S, entropy, and we let go, that entropy will change in one direction. Okay, let's have it grow. Mathematicians like to have it go down, engineers like to have it go up. I see myself more as an engineer probably, so I have it go up. So the entropy of the system goes up, up, up. It changes over time, going up. But then when we reach the final equilibrium state, things get stuck, right? No change anymore. So then the change must stop. So it must be such that as long as the system is not in equilibrium, we have the larger than zero sign. And then in equilibrium, we have the equal sign. So the entropy of an isolated system, we do nothing, just evolves, growing until the change stops. So in the final stable state, the entropy is at the maximum, and the entropy generation rate, which I introduced here as S dot gen, which will be a very important part of our discussion, becomes zero. In non-equilibrium, as long as the process continues, we have entropy generation, and this is why the entropy changes towards the equilibrium. It's an equation, it describes this. But now we have introduced things that we have to fill with meaning. What is entropy now? Well, it's a name, it's a letter. So we have to find information about it. So first of all, this was just for the not isolated system. So of course, we are not interested in isolated systems. We are interested in technical systems which exchange heat and work and mass. So we have to generalize for those. And we have to say something about entropy. Right? So recall that when we had the first law, we had to say something about energy in terms of things we can measure. Temperature, for instance, here on the examples. Or density. Okay, so we're just starting. But we do this fast. We only have 3 hours, so we have to jump a bit. So let's look at the non-isolated system. It's closed, so all we can do here is we can exchange heat, we can exchange work in probably 2 ways. We can move the piston or we can move the propeller. And Now, if we do things like this, if we put work in or out, or put heat in or out, this is all we can do, but we must expect that if we change the state of the system by doing something like this, transferring work, energy in the form of work or heat, that this will also change this unknown property, which we call entropy. Right? So there should be some change of the entropy of the system associated with this. And here comes a big jump, which saves us probably half an hour. I just put in these terms that describe how entropy is traveling with heat. And I will go the other way around. I will show you that this indeed is what we need to ensure that heat goes only by itself from hot to cold. And because there is no limitation for work, heat goes from hot to cold. So we need something in the equation to make sure that this is what happens. But since work is not restricted in direction, we can transfer it any which way, we cannot have a work contribution to the second law, but we must have a heat contribution to the second law so that we can ensure that heat goes from hot to cold. Right? So that we only have a heating term here, a heat transfer term in the second law, is due to this fundamental difference between the transfer of work and the transfer of heat. And what do we have here? We have Qk, that is the heat that crosses the system boundary at a point where the system boundary has a temperature Tk. Right? So you can imagine that your system, of course, has inhomogeneous temperatures, so also the system boundaries will have inhomogeneous temperatures. So you find the location where you transfer the amount Qk and you look at the temperature Tk of the system and you divide the two, and then you add it all up over the whole system boundary so that you have everything in there. Right? So again, this is postulated for time, but we will see that it has all the features we want. Okay? So the first thing now, before we even go and evaluate this to see that this is the right term, we look at entropy in equilibrium. We need to find a way to measure entropy. We have to relate it to stuff that we can measure. And how does this work? Well, we consider what we call the quasi-static process. Here's where we need this. So we have a very slow process changing. The system goes from one equilibrium state to the next one. And then the first law changes drastically. Or not drastically, but simplifies considerably. Right? So instead of having all the energy, all we have here, which was internal plus kinetic plus potential, we only have the internal energy here, the thermal energy. Well, if you stir your system, you have kinetic energy in your system, but you know quite well, then you have a non-equilibrium process and a non-equilibrium state. A stirred system with different velocities everywhere inside cannot be in an equilibrium. It's in an inequilibrium, in a non-equilibrium state. So we have to assume this quasi-static process from the start that there is no kinetic energy. So everything is at rest and you change things very, very slowly. Right? No propeller work for the same reason. If you put in a propeller work, you create a velocity gradient within your system. You have a non-equilibrium process, you can't do it. But what you can do is you can squeeze your piston slowly. And this is the volume change work, right? Force on the piston times the rate of change. And so your first law for the quasi-static process is simplified form. And also your second law, our second law, simplifies because all this entropy generation describes the need to go to equilibrium. There is entropy generation until we go to equilibrium, and then the entropy generation vanishes. So if we are in equilibrium process, we are in equilibrium states at all times, there cannot be entropy generation. And there cannot be inhomogeneous temperatures. So there's only one temperature for the whole system and the boundary of the system. Q is the overall heat flux leaving or entering the system, and no entropy generation. So this looks so much better. And now you see, for the internal energy, we have knowledge. We understand that we can go and measure it. We have the thermal equation of state. For the pressure, the caloric equation of state, for the pressure, we know we can measure it, independent of density and temperature. We have the thermal equation of state. So everything in here we can measure. Entropy is what we don't know. Heat we can eliminate between these two equations, which we do. We multiply by T, we subtract, and we eliminate Q, and we find, from looking at equilibrium processes, what is called the Gibbs equation, which is a fantastic equation which we will go and explore further. So this is a big step for the second law, is to find this equation, which is universal. It has nothing to do with the material you're looking at. It tells you how in a system the entropy changes if you change energy and volume. And you have to know something about pressure and temperature. And so this is universal. Every simple substance has to obey this equation. And of course, we use it by integration to find the entropy. Right? We know energy, we know volume, we know pressure, we know temperature. We bring temperature to the other side, we integrate, and we have entropy. Like here. Right? So this is mass divided, the small letters, small s, small u, small v are by mass. You have an incompressible liquid. You know the volume is constant. So this term vanishes. You know the energy is specific heat times temperature. Well, du is specific heat times dt. You integrate, you put in a reference value at T naught, which you call entropy at naught. And you have a direct function for the entropy in equilibrium between temperature, which you can measure, and entropy, which you just introduced like 5 minutes ago. Okay? So no problem. You have to go and measure the specific heat. But that's the first law question. We assume that we can deal with the first law. For the ideal gas, it's a bit more interesting. So the pressure depends on density, the gas constant, and temperature. Specific heat also is a function only of temperature. The internal energy is a function only of temperature. I assume constant specific heats even. I put all this in, I integrate, and I find the entropy as a function of temperature and volume with logarithms here and here. So it looks a bit more complicated because the volume change, specific volume change, affects the entropy. Okay? Of course.
What was C?
C is the specific heat. This is the factor that stands between energy and temperature. I forgot to put a V here. Right? It's just, you go and measure, it's a specific heat. Essentially, it tells you how much energy you have to put in to affect a change of 1 degree for the body temperature.
And what gives U?
U is the internal energy, the thermal energy of the system. Yeah? Okay. Good. So these are just examples. You have the Gibbs equation. As I say, it's fundamental, it's universal for all simple substances. And simple means there is no change of composition by reaction or anything. And we have it at our disposal. Right? We just have to go and integrate. Or people like to use a TS diagram to draw processes. We will do that in a bit. The TS diagram is interesting. It's also meaningful for these quasi-static processes because the Gibbs equations tells us the change of entropy is du plus pdv, and this is what we know from the first law. So the change of entropy is, for these quasi-static processes, related to the amount of heat we transfer dq. So if you have a quasi-static process running through all these equilibrium states, you know the process curve in the TS diagram. You can find the area below the diagram, below the curve in the diagram, and you know this is the heat. It's useful to know from time to time. But this is not what we're after. So we have entropy at our hands. We can measure it indirectly by using equations of state and the first law and the Gibbs equation. There are these constants of integration which are discussed in the third law of thermodynamics. So we have this, and now we can go and look at whether this equation actually does what I said it would, which is telling us, for instance, that heat will go by itself from hot to cold and not vice versa. So how do we do this? Well, we look at the simplest thing that we can have. We have a hot reservoir, just a hot body. We have a cold reservoir, just a cold body. And in between, we have our system. This is the system we're looking at. And this system exchanges heat with both reservoirs, the hot one and the cold one. And it takes in the heat QH at the hot reservoir. It takes in the heat QL at the cold reservoir. And I put both arrows in just to indicate the typical use of the heat. Heat into the system has a positive sign, right? And this is all what happens in the system. So there's no work, nothing else happens. And so if you write our first law, this is what it says. The change of energy of the system, and again, the system is the heat conductor in between the two reservoirs. The change of the energy of the system is due to transfer of energy, which is no work here, but only heat with the exchange with the cold reservoir, heat exchange with the hot reservoir. And the second law now has these Q over T terms, and two of those, one for the cold reservoir and one for the hot reservoir. Right? So all this adds up to the entropy generation, and we demand that the entropy generation has a sign, is non-negative, to make sure that we have this approach to equilibrium that we're looking for. So in steady state, where nothing changes anymore, right? So we have the reservoirs are big, so the temperatures TH and TL are not changing, and so at all points in time we see the same. Then there is no change of internal energy over time. There is no change of entropy over time. So no derivatives to deal with. And you see the first law just tells us QL is minus QH. Here. We just call it Q dot, the overall heat. So the heat that comes in here must go out there. QL being negative means it goes out. QH being positive means it goes in. And the second law, we can, because now the heats are the same by magnitude, only different in sign, we can take the heat out. And the second law now is Q dot times the difference in inverse temperatures must be the entropy generation and should have a sign. Now, by definition, TL, cold, is smaller than TH, hot. So 1 over TL is larger than 1 over TH, so this bracket here is positive. And so in order for the entropy generation to be positive, we need positive Q dot, which was equal to QH, the heat coming in. So the second law tells us this heat, Q, this is equal to Q. This heat must be positive. And QL, therefore, must be negative. So we have to take heat in at the hot and discharge heat at the cold. So heat goes from hot to cold. This is what we wanted. This is what where the Q over T term in the entropy law, in the second law, actually comes from, to make sure that this happens. Okay? So the equation does what we want. And this, again, is the time to say that there is no preferred direction for work, and so work does not show up in the second law. Yeah? That's what it is.
But the system never reaches an equilibrium, right?
Say again?
The system never reaches an equilibrium.
This system never reaches equilibrium because you maintain the non-equilibrium by having different temperatures, right? Because if we assume that the reservoirs are infinitely big and always at the same temperature. Yeah, would they be of finite size? They would cool down. As you take heat out of the hot reservoir, it would cool down. As you put heat into the cold reservoir, it would heat up. So you would have, in the end, by means of the transfer of energy between the hot and the cold, you would have equilibrium homogeneous temperatures between both reservoirs at the very end. But as long as we assume that we have a steady state, say infinitely big reservoirs, hot and cold, then you will never reach an equilibrium state. The system, what happens is the process tries to bring the system towards the equilibrium state. You just, by keeping it hot and cold, we prevent it from reaching it. Right? And so here is it in a picture. The left, heat goes from hot to cold. This is allowed. The right is forbidden. Heat will never go by itself from cold to hot. We can do something to do it, and we'll look at that. But this is what it is. Okay. Friction. Remember our stirred coffee? So let's see that the equation describes this as well, right? So we want that the coffee, when it's in motion, spoon is out, will reach the final equilibrium state, which means come to rest. Okay, so we take our coffee. Here is just a very simple picture. Just keep in mind that each little element of the coffee has different velocities, right? The coffee swirls after all. But so there's a total kinetic energy for our cup. Just integrating the kinetic energies of all the cells, velocity squares, over the volume of the cup. Here's our first law. We do nothing to the cup. It just sits there. No heat exchange, no work. The spoon is out. We stopped stirring, right? It's just moving. So the energy law just tells us, the first law just tells us, internal plus kinetic energy will not change. The sum of kinetic plus internal energy will not change. Well, and again, as I said, this does not forbid that kinetic energy goes up and internal energy goes down, but the second law does, and we have to see how it does this. So this is the isolated system. The entropy must increase towards the equilibrium. So now we have two equations, and we have to relate the two to find out how the system as a whole behaves. Well, keep in mind that we had the Gibbs equation, which tells us that in this case we have no volume change. The change of entropy with energy is the inverse temperature. So let's use this. So let's say, okay, the change of entropy this time is a change with entropy with energy times energy change with time. So we just use the chain rule. Well, we know the SDU is 1 over T, so here's a 1 over T times the change of the internal energy, but we know from the first law, that if internal energy goes up, kinetic energy has to go down because the sum of the two stays constant. So the change of kinetic energy, internal energy with time is minus, here's a minus, the change of kinetic energy with time. So minus 1 over T, the change of kinetic energy must be positive. This is what the second law, combined with the first law, tells us. Right? So we know kinetic energy decays. This is what we know. Daily experience with our coffee. And so we want it to go down. And because the kinetic energy is a square of velocity, it cannot go down further than 0 where the velocity vanishes. And in order to have this, right, so the change of kinetic energy is negative. Here's a minus sign, so the 1 over temperature must be positive. So this is a final point here that, in fact, this wants temperature to be non-negative. So this temperature, and I don't say much about it because of, again, of time issues. This temperature that appears in the second law, which is this temperature, this is what we call thermodynamic temperature. It must be positive in order for this to happen. It cannot be negative. Thermodynamic temperature has a sign. It's positive, and because it's positive, or when it is positive, the second law tells us that our stirred coffee will come to rest. Okay?
Can I have
Yes.
a question?
Yes.
In the assumption of being homogeneous, what's the cycle between this?
The assumption of homogeneity is just for making things simpler, so that we don't have to deal with integrals. So it's very, very good. It's good eyes. So to make things simple, I said, okay, there's just one temperature for the whole system. Else you would have to go through all inside the system and look at PDEs, which certainly we don't want to do here, right? So simple assumption, we assume, the temperature is the same everywhere, and then we can deal with it like this. You could go into the detail, you could go inside. Good. I'm talking, time flies. Good point to ask. Any other questions?
Well, I think you derived the Gibbs equation with the assumption of equilibrium.
Yes.
And you applied it now on the non-equilibrium process, so you have...
Yes, that's a very good point. Can we apply the relation between entropy and the other properties which we found from looking at equilibrium, can we apply it in non-equilibrium? We will come back to that at the very end. You can for some processes, but not for all. So Manuel smiles. What Manuel and I do together is what happens if this cannot be done anymore. But there's a wide range of processes where indeed you can assume that, at least locally, the property relations that are valid in equilibrium are valid locally. So this is called the local equilibrium hypothesis, and it's limited in range, but if you are someone who uses the Navier-Stokes and equations, Fourier's law of heat conduction, you apply it every day. Okay, we come back to that. In fact, I have some slides on the Navier-Stokes if I manage to get there in time. Other questions? Okay. So here's our second law again. We have to show it more than once. We have to keep reminded that this QK means heat transferred across the system boundary at TK. If you want to resolve it finer, you would make it an integral, of course. So this second law, now what does it mean? Right, so we found it, if you like, by generalization of our observations on coffee. So now this law describes the desire to equilibrate, right? You always want to go to an equilibrium if the system can. So this can be considered as a force, right? So there is a strong desire to go to equilibrium, right? Heat wants to go from hot to cold. It really, really wants to go from hot to cold. So if something really, really wants to go, it can drag something, right? So if you really, really want to go to dinner, you drag your colleagues along, right? So you have a force, you're hungry, and you pull the other guys who could still wait half an hour. So the same here. If you have a strong desire to equilibrate, you can build a machine, an engine. And this is what thermodynamics, technical thermodynamics, engineering thermodynamics is all about. It's about heat engines. A heat engine harvests the desire of heat going from hot to cold. You provide a hot space, you burn a fuel essentially, and make something very hot. And then the heat wants to go to a colder spot, typically the environment, and there's a strong desire, you put a machine in between, an engine. You put hydrogen and oxygen together, they're really keen, if you allow them, to react to water. Right? You have to put something in there to make it happen. You can make a fuel cell, for instance. We will talk about heat engines, fuel cells in a bit. That milk really, really wants to mix with the coffee. So if you're clever, you make an engine that harvest the desire for mixing. I will talk later about what we call osmotic power engines. So this is, you take salt water obviously is water and salt coming from the ocean, and that salt water wants to mix, you bring it in contact with river water, that salt wants to distribute over all the water that's there, river water and salt, seawater. So something is happening, and so you can, strong desire to mix, you can use this, right? So we will see in a bit that when all processes are reversible, the work harvest is maximum, and irreversibilities reduce the output. And this is the other thing that engineering thermodynamics is about, is quantifying and reducing irreversibilities anywhere in your system. We will quantify that in a bit, okay? So the next slide will look pretty similar, but will describe the opposite. So again, just to say, the desire to equilibrate is a force that we can use to our benefit. So this is the opposite slide, looks pretty much the same in color. So, but now if you want to do the opposite, so you want to maintain or create a state of non-equilibrium. You want to make your coffee cold, or your ice cream, or you don't want to spoil your milk, you put it in a refrigerator. What is a refrigerator? It takes heat from the cold and moves it out into your kitchen, right? That will not happen by itself. We made very clear of that looking at the second law. The second law will have heat going from hot to cold by itself, so you have to do something to override it by itself. You have to do something, you have to put in energy, work typically, to make it happen, right? So you have to act against the force, right? I'm not hungry, I stay here. You chain yourself to the chair, and your hungry colleague has to wait. Work must be provided to create and maintain refrigerators, right? You make a cold spot in your kitchen by building a refrigerator, heat creeps in through the insulation, and you have to bring it out again to the kitchen. You want to split water into hydrogen and oxygen? Well, you have to do something. In this case, you have to build an electrolyzer. Or you want to separate stuff. And if you look at chemical industry, oil refineries, that's all they do. They separate different carbohydrates. Or if you like spirits, like cognac, you separate the good from the bad, the water from the alcohol. Or is it vice versa, the alcohol from the water? Right, so you use distillation or use membranes to split stuff. But this will not happen by itself, because the ideal state where the system wants to be is mixed. So you have to act against the desire, right? So you have to put stuff in. So in this case, you have to provide work, and work that you get out of your system is positive. Work that you have to provide is negative in the conventions I use. So in absolute value, when all your processes are reversible, the work input is minimum. But any entropy generation that you have, and if you look at these, we have to look at these, any entropy generation that you have in your system will increase the work you have to put in. You need some work to separate anyways, but now you do it in some irreversible way, you will have to put more work in. So that is a crucial element of engineering thermodynamics. Okay. This is the longest equation probably, or the second longest equation that I show you. I like to start talking about the closed system because it's so easy. Probably I could have started here as well. So this is an open system. The only difference is that the open system has open boundaries, so matter can enter and leave. Right? We have some mass flows coming in. We have some mass flows going out. And if you put mass into our system, mass carries energy, so you put mass into the system, you put additional energy into the system. You take mass out of the system, you take energy out of the system. So there are terms here that account for the inflow of energy with mass the outflow of energy with mass, and these two terms you already know. And there's this quantity H showing up here, which I defined. I did not even put the name on. It's not nice. It's called the enthalpy. It's energy plus pressure times volume. It just shows up because you need work to push the matter in, and you need work to push the matter out, and that work shows up, combines with internal energy into this term here. Again, I leave it at that. So open system, you bring energy, and that is internal energy, kinetic energy, potential energy in and out of the system, and you need work to do that, hence enthalpy, not energy. M dot is the mass flow, the amount of mass crossing the system boundary per unit time, here or there, or here or there. And just as matter carries energy, it carries entropy, right? We use the Gibbs equation to compute how much. If we send mass into the system, we carry the entropy of the mass in. If we take mass out of the system, we carry the entropy of the mass out. So that's the only change. We need this from time to time. Maybe, let's see, I'm not even sure that I know all my slides. But this is, engineering-wise, if you like, the crucial thing. This one. Work loss. Yeah?
A question, mass in and mass out here, and the energy, is this mass staying in the same nature, or is it going through reactions?
Whatever it does, whatever the state is, it really depends on, so what the mass is depends on the boundary conditions, how I control what's going on. Whatever happens inside, I might send in hydrogen and oxygen and get water out. Whatever might happen inside, might happen outside. We have to make sure that we know, we define the system that we look at, we define the system boundary, and then we have to find out what happens at the boundary. What is the state of the matter that comes in or out? Yeah? Okay, two equations. So, if you go to old thermodynamics books, engineering thermodynamics, you will not find this argument. So this is something that comes more, it's not that old, it's not that new, but the argument in the textbooks you find more in the last 20 or 30 years and not 50 years ago. So, think about how we live. We live in this almost perfect world, or maybe not so perfect world, but we always are exposed to an environment, right? First thing you do in the morning, you check your cell phone for the weather. In the old days, you open the window, but now you check your cell phone. And so the outside, how it is, plays an important role for us, and we take it for granted. And we have to take it for granted because it's big and it's there, and we live in it, and we will always interact with it, okay? And if we put a little bit of heat into the environment, on the big scale of things, that doesn't matter. If we take a little bit of heat from the environment, big scale of things, it doesn't matter. We will not affect the temperature of the environment by sweating, for instance. So we take the outside environment as something very big. It's for granted, it's for free, we don't pay for it. We can damage it, I will not argue. And sometimes small things matter, like when we put all that carbon dioxide in. But as a heat sink or source, whatever we do is small fries. So every system we build, every heat engine, car engine, refrigerator, will somehow communicate with this big environment which is there for free. So, of all these, when we look at a system which is in thermal contact with many reservoirs, many different things, one of them typically, normally, will be the environment. And the environment is for free. So we call the heat exchange with the environment, we call it Q naught. The temperature of the environment we call T naught. And in our two laws, the first law and the second law, they're still here on the previous slide, right? We have the Q, and now the Q is the sum of all the different heats that we exchange in our system at different temperatures, different boundary temperatures of the system. We single the heat with the heat exchange with the environment out. We do the same for the second law, right? In the second law, we have the sum over the Q over T terms, and we single one term out, which is the heat exchange with the environment, and T naught is the temperature of the environment. We don't care. It's not a cost. We will not be interested how much heat we put in or out of the environment, so we eliminate it. And so we eliminate it between the first and the second law, right? So we have two laws which always act together. We have to bring them into contact somehow, and we do that by eliminating the heat exchange with the environment, and then we turn the crank, simple algebra, and we solve for work. Because work normally is what we're interested in, so we open now the sections where we go towards engineering processes. We're interested in work, right? If you build a power plant, you're interested in electricity generation, right? A 500 megawatt power plant, yeah. So the W dot would be your 500 megawatt. You want 500 megawatt? There you go. You build a car engine, right? Same thing. And if you build a refrigerator, or vacuum cleaner, or coffee maker of course is important, you have to put work in. You have water, right? So you want to make it hot so that your coffee is nice and hot. So, or refrigerator, right? You interested in your electricity bill. So work is the central quantity that we're interested in. So we solve the combined equation. We eliminate the heat exchange with the environment. We solve for the work. And the first term here, this is the interesting one. This is the entropy generation, which we have in the second law, which if you look back, we haven't said much about, right? We just said it's there. We just said it has a sign. We just said it will vanish in equilibrium, but else we didn't say anything, right? So there is a gap in the argument for now, because we will have to specify the entropy generation. So this first term has a minus sign. T naught is a thermodynamic temperature, right? Recall, the temperature must be positive. And the entropy generation must be positive. So this term, T naught times the entropy generation, is positive. With the minus sign, we have something negative. Without the minus sign, we call it the work loss. And here's the reason. If we look at a system that produces work for us, or a power plant, we want work out. If we have entropy generation inside the system, we compute it by all this, and then we have to subtract the work loss, right? So the entropy generation reduces the amount of work we get out of the system. We want as much work as we can, but if we have lots of entropy generation, and now, I mean, look back. Did I say the word friction? I probably didn't say the word friction. That's bad. When our stirred coffee comes to rest, this is friction. Friction slows down the coffee. So friction overall destroys work and makes heat out of it. Rub your hands, gets warm, the work is gone, but you have created thermal energy. So friction, heat transfer over finite temperature differences, all these things, and we will look at it in the next slides, I think, create entropy and reduce your work. Right? So anything that creates entropy in your system, you have to identify, you have to reduce, and you get a better device. That's the engineering task. Identify what creates entropy, think about how you can reduce it, or how you can change your system. The power plant is a big thing. How you change it to reduce the entropy generation. Now, if you have a system that needs work to run, like your refrigerator, you have to put work in, which means the work is negative, then this terms still has the same sign, right? Positive temperature, positive entropy generation, and a minus sign. So this means there is more work to be put into the system so that the system actually runs. the more entropy generation you have inside your system, the more work loss, the more work you need to overcome irreversibilities, the more work you have to provide. Right? So entropy generation is a thing. No entropy generation, everything is reversible. Yeah, you will not manage. Right? So every process is irreversible. So you have to make sure to make it reversible. So here's a list, right? So again, any work loss is bad. And here are the things that happen: heat transfer over finite temperature difference, friction, uncontrolled mixing, uncontrolled reactions, and so on. Right? So the goal, redesign, and of course the general goal is you just want to understand what's going on. And we need to understand entropy, we need to understand entropy generation. Okay, questions here? 90 minutes is long. Okay. So let's start with heat transfer, right? So essentially, I work through parts of the list, other parts will come later. Let's talk a bit about heat transfer and friction. You know, of course, you all are technically inclined. You opened up a computer and you know that your computer has to shed heat, right? You have to get rid of heat somehow, and you have heat ducts and you have heat exchangers in your computers, and the bigger and more powerful your computer is, the bigger these things are. So heat transfer is an issue, right? You want to get heat out or you want to get heat in. Heat transfer creates entropy. We saw that before, right? We have heat going from hot to cold, and this is in fact a case where we know the entropy generation from what we did before. We just would have to go a couple of slides back, and we would find this expression for the entropy generation. So for heat transfer, actually we know how to compute the entropy generation. So entropy generation, if you want to know it, depends on the process. You have to find a way to solve it. So Newton, he knew nothing about energy, entropy, and those things, but he was clever nevertheless. He noticed that heat goes from hot to cold, and he wrote down what is called Newton's law of cooling. So you have a temperature difference that will affect a heat transfer, and there's some proportionality factors, of course, for the units and size. And alpha is the heat transfer coefficient, and A is the contact area between the two systems or the two elements that exchange heat and are at different temperature. Right? So A is the contact area. So if for a given temperature difference and a given heat transfer coefficient, you want to get more heat out, you make the cross-section larger, and that is the dilemma of heat transfer, right? You need large cross-sections, and then you manage much better. So if you combine Newton's law of cooling, you can even say, oh, okay, let's look at this. If I plug this in here, I see, or if I want this to be valid for any heat transfer, this is a way to look at it. You want to say, okay, we ended up with here, but we didn't say anything about Q. You would say, okay, I know this must be positive, heat times difference in inverse temperatures. What expressions for the heat transfer would make this always positive or zero when the temperature difference vanishes? And you would come up with this, right? So you could even use the second law to argue for Newton's law of cooling, and that there's a cross-section is essentially common sense. If you put the two together, here's the entropy generation. You see the entropy generation grows with the square of the temperature difference. So in a heat transfer. So if you want to have effective heat transfer, or effective in the sense of little entropy generation, you want a small temperature difference within your system. Right? So if you build a heat engine, you transfer heat, you want a small temperature difference between the two bodies that exchange, or the two parts of the system that exchange heat. Small temperature difference means large cross-section, right? To get the same amount of heat transferred. So heat transfer is not an easy thing. And it's highly irreversible unless you really go to infinitesimal temperature differences. Then it's, if in square of an infinitesimal number is negligible, then you can say heat transfer at infinitesimal temperature difference is reversible, but else it's not, and the entropy generation and therefore the work loss goes with the square. Okay? So heat transfer is bad. And one thing to see this is, why is there work loss? Well, if I have a finite temperature difference, I could take a heat engine, put it in between, get work out, and because I do not do that, I have a loss, not realized. So there's a desire which I could harvest to do work, right? A strong desire to transfer heat. I could harvest that to run an engine, but I don't do that, so I have a loss. The loss is related to the entropy generation that happens instead. Flow friction. This is too many equations. So I will only show you the results. The mass flow is related to a pressure difference. So you need a pressure difference to overcome friction. And typically, if you have lots of pipes, right? So you have lots of pipes and systems. So all these pipes, you lose pressure in the flow. So this is another irreversibility. Little you can do. Turbine and compressors, so this is a bit technical. And this TS diagram. So this is one of the steeper slides. Maybe this is people who did first thermo courses, engineering thermo know all this very well. So what is a compressor? A compressor is a spinning device which takes gas in and compresses it to higher pressure. So because this goes fast, this goes really fast, the gas that goes through the compressor spends very little time in the compressor, and therefore has no time to exchange heat. If it has no time to exchange heat, then there is the process is adiabatic, and if you look at the second law, right? Can I do this? So this is steady state. So no. We can write the relation between heat transfer and entropy change in the reversible process. As the heat exchange is TdS, so in a reversible process, the entropy would stay constant. If there is no heat exchange in the reversible process, there is no exchange of heat, no change of entropy. If the process is irreversible, because entropy can only grow, the irreversible device, the irreversible compressor in this case, will have an increase in entropy. Therefore, it's a great thing to look at the entropy temperature diagram. We have two lines of constant pressure here, low pressure, high pressure, and the compressor sends the gas from state 1, some initial state, to state 2. Would it be a perfect compressor, a friction-free, perfect compressor? The entropy wouldn't change because there is no time for heat exchange, and therefore the entropy would stay constant. But because there is friction, there's an increase in entropy, which is noted down here. And this comes from essentially, friction inside other processes inside, mainly friction, I would say. And because there is friction, you need more work to put in to compress as compared to the reversible compressor, and you end up at a higher temperature, right? So this is a temperature diagram. So your point 2 is at a higher temperature because that friction that is in the system makes it hotter. And for a turbine, it's the opposite. You expand, you have a high pressure gas, you expand it to low pressure, but you have friction, you end up at higher temperature, you have entropy generation, and you get less work out than you could in a reversible system. Yeah? So the irreversibility makes the output hotter in both cases, makes the work output of the turbine and the work is smaller and the work requirement of the compressor larger. So friction, this is what it is. There's a throttle, let's not talk about it. So maybe it's time. Should we do the break now, or you want to go through heat engines for a while? I'm hot, I feel the heat. We can, or we go another 7 minutes. That might bring us to another good point to stop. That's a joke I found online. It's good fun to look for jokes on entropy and the second law. So this guy invented a perpetual motion engine, but there's one snag at one start. Perpetual motion engine is any engine that violates the first or the second law, right? So the second law, the first law together, they limit what can happen, and we have to live with that, and we have to make our engines as good as we can. We have to understand where entropy is created, and we have to do about it as much as we can, right? If you go back to the compressor and the turbines, there's only so much you can do. There will always be some irreversibility related to these systems. You can probably use CFD and things to make your engines better and better, but not to the end. So let's look at heat engines in general first. So this is what a basic heat engine is. You have, again, something hot and something cold, and we put the engine in between, and I use absolute values here in the picture, but not in the equations. We take heat in at high temperature, we reject heat at low temperature, and we produce work. So we do that steady state. So the first law just tells us that the total sum of heat in, heat out, and work must add up to 0. No change of the energy of the system. And the second law tells us, well, heat over temperature minus heat over temperature must be positive. Right? So we have to live with both. So again, we have a case where we have to deal with both laws at the same time. Essentially, we do what we did before. We eliminate what we don't care for. What we don't care for is here the heat that we reject. That heat goes to the environment. The environment is there. It's big. We take it for granted. What we pay for is the heat that goes in. We pay for fuel. We pay for coal. We pay for oil. We pay for gas. We pay for uranium. We pay for how much heat we can put in by buying the fuel. And what we want is work. We want to push our car, we want to make electricity. This is what we get. But we don't care how much then is left over, because we only care for these two. Okay? So what we do, we take the first and second law and we eliminate once more what we do not care for, which is the heat QL, the heat that we dump in the environment. And we get a simplified form of the equation we had earlier. Work is related to the heat that we pay for, the heat we pay for the fuel times this factor, which is called the Carnot factor, minus, here again, is our work loss. And what people like to talk about is what's called the thermal efficiency, which is what you get, there's a dot missing, over what you pay for. What you pay for is the fuel, what you get is work. And you see here, the entropy generation shows up. It is important. And if you have a fully reversible engine, you come up with what is known as a Carnot engine, which is a lot always discussed in thermo books. So it's a fully reversible engine between two temperatures. But you have to deal with the real thing, right? Here we are again. Thermal efficiency has to do with the temperature difference, has to do with the entropy generation. You see, because of this minus sign, any entropy generation in your system makes the efficiency less. Right? Less work because of losses. But even if the entropy generation is 0, your thermal efficiency is not 1. You need a temperature difference to drive the process. You need 2 temperatures, not just 1. And both temperatures show up in this ratio, TL over TH, so you can never fully convert heat to work. Right? Because you need a potential difference, if you like, that drives the flow. The flow of heat that then runs your engine. If the upper temperature is higher, TH, you see you subtract less here from the 1. So high temperature heat has more value. So typically you want to go to really, really high temperatures. And, well, irreversible processes reduce the work. I said that more than once by now. Yeah? So here we have a little picture of what is forbidden and what is allowed. And we can, of course, take work and destroy it into heat. Right? Friction, again, we rub our hands, this is what we do. But we cannot go the other way. Let's stop here and make a break. Okay, so where are we before we take the break? We have found the second law. We still don't know why it rules, but we understand that it rules, that it's there. We have control, we can find entropy. We understand that entropy generation happens because of heat transfer or friction. We will see it shows up because of mixing reactions, other things. And we understand basically from here, for example, that entropy generation in the system reduces the efficiency. It gives us less work output, or it requires more work input. We look at that. The outlook is this. We will start with simple engines. We will look at the car engines. We will tell you why there's a Atkinson and not an Otto motor in hybrid cars. We look briefly at steam power plants. We ask why jet turbines get wider and wider over the years. I will explain that. It's all related to the second law. And after that, we start to talk about mixtures. And when we talk about mixtures, we will also start about what entropy, or how we can, in simple terms, understand what entropy actually is and why we observe this trend to equilibrium. So we go a bit deeper into matter. But you see, you can get far without knowing what entropy actually is. You don't know what energy is for that matter or why it is conserved, right? So people are always nervous. What is entropy? What is energy? Well, kinetic energy, whatever. And why is it conserved? You just live with it and you use it, and this is what engineers do. But of course, scientists want to understand better, and as a scientist, you then go into the microscopic and you understand what energy or thermal energy is from the microscopic, and you understand what entropy is. So we will go there. I run you through a couple of technical processes before going there. It's essentially, really, I went through the book and let me guide from that. But in the end, I hope it will be interesting. Any questions for everyone before we take a break?
At the equilibrium, entropy generation is 0 and entropy as well is 0 or not?
Say that again.
At equilibrium,
At equilibrium?
the entropy is 0 or not?
No. The entropy at equilibrium has a value which depends, the entropy generation vanishes. No entropy generation, but the entropy has a value because we have the relation between, we have the Gibbs equation, or we integrate the Gibbs equation, we find where is it? Long ago. We find property relation, right? You see, at reference point is naught, the way it's made, the entropy has at temperature T0, the entropy has a reference value that we prescribe, and at other temperatures at different values. We will use absolute zero to properly define the reference point, but else entropy always has a value. Entropy generation vanishes. Okay?
In the heat engine efficiency, the efficiency equation, you've got the low temperature times entropy generation.
Yes.
Well, maybe that isn't this. Why is it the lower temperature?
This is, the short answer is it's just mass. I'll show you. We eliminate QL,
Ah, okay.
right? And because we eliminate QL, it's here.
Okay.
This is why it shows up. Yeah? Anything else?
Yeah, in the last picture, you showed this same scheme, but with no QL going out, and you said that it's not allowed.
Yes.
But I didn't get what.
It would give you, where do we see this best?
Yeah, this
We would have to go, yeah, that's a good point. It's not visible from here. You can see it from here. If QL is 0, right, you have the entropy generation is minus QH times TH. TH is positive. The entropy generation must be positive, right? So if you, would you not have this term, right? This minus Q times T must be positive. That means Q must be negative. Q cannot be positive. So if we go to this picture here, in this picture QH is negative. The absolute value goes out of the system. Heat leaves the system. That is allowed. But here, where QH is positive and no QL, you cannot fulfill the second law. This would give negative entropy generation and cannot be.
So there are always laws. There is
Well, it's not a question of loss. Even if you have no loss, you cannot. I wouldn't say it's a loss. It's a matter of it's a question of language, right? So you cannot fully convert heat into work. It's not a loss because nature doesn't allow it. If you do worse than nature allows you to do, then I would say it's a loss, right? So the entropy generation, this is really a loss. This is what you have to live with, right? So in the best case, you have this efficiency, and this is as good as you can be. No loss there. It just tells you just have to accept you cannot fully convert heat into work. But if you have entropy generation, you really have a loss because you are not doing as good as you could do in a perfect system. Okay? More questions? No. Okay. How long is the break typically here? Until 3. So we take a break until 3, and then I hope you'll be back. Thank you. Let's continue with this question. Heat engines. And we agreed that entropy generation is a problem. Right? Entropy generation reduces power output of a heat engine. So let's talk very briefly about internal combustion engines, right? You have an internal combustion engine in your car. If you have a car, you hopefully know how it works. The good old days, people used to know. Now you know better about your computer operating system, I guess. So what you have is a piston going up and down. Oops, I lost my pencil. Hello. You have a piston going up and down, and what you do is you start here at the top, that center, you open a valve, and you draw fresh air in, or rather what you draw in a typical car engine, not a diesel engine, is a mixture of air and fuel. You evaporate the fuel into the air, and you draw in air-fuel mixture up to top dead center. You see that here the pressure is just the external pressure. You draw from the small to the large volume air-fuel mixture. And then you close the valves, and you push the piston in. It's just on the crankshaft, and the crankshaft forces the piston in, and that increases the pressure, and then at some point you put the spark on to start the burning of the fuel, which is very fast, and because it's fast, you get all the heat energy out. You heat up the air gas mixture, combustion product. Now the pressure goes very high because of all the energy that you supply. It gets hot, and the pressure gets high, and then the piston is pushed from. So we are back here, right, compressed, and now we have this very hot stuff up in here in the small compartment, and it's hot, and it violently pushes the piston down. The pressure goes down, the volume goes up, and this is where you get the work out, really. And then, as you reach bottom dead center again, now you have spent fuel air mixture in your cylinder, and you want to get rid of it. So you still have high pressure, high temperature gas. And what you do is you open your valve, and you have the pressure drop, and you push the hot gas out. Right? So now if you think about what we said before, entropy generation is bad, you have to understand that this process is, that entropy generation is attached to this process, because what you have here, the high or increased pressure, high temperature gas still has work potential. You can run it to lower pressures. You could use the temperature difference between the gas and the environment to do work, and all you do is you throw it away. Whenever you throw away stuff, you know you create entropy, as a rule of thumb. So if you have the typical car engine, here it is, the Otto engine, the intake stroke and it should say compression stroke, I apologize. The compression stroke and the expansion stroke are the same, right? It's just like here, you go up and down between top and bottom dead center. So it's a classical engine. And you have a problem here, which is that the temperature is, as you compress, the temperature goes up. This again is a process which goes very fast, so there's no time for heat exchange. So in good approximation, you treat it as being at constant entropy. So the temperature goes up as you compress. You compress stuff, you put work in, that work increases the energy, so it gets hot. But this is a fuel mixture you compress. If it gets too hot, it will just start to burn. So you cannot compress it too much, because as soon as you reach what is known as the outer ignition temperature, the temperature of the mixture at which it starts to burn right away, you have combustion while compressing, which is destroying your engine and certainly is not giving you the work. So therefore you are limited in this compression stroke from 1 to 2, how far you can actually go. And therefore your compression ratio, your volume ratio between 1 and 2 is limited by the outer ignition temperature. And how high you can go with this compression ratio depends on the type of fuel you use. If you have normal fuel, normal gas, it's 8. If you have super duper fuel, you can maybe go to 12, but you cannot go higher. And just by construction, expansion stroke is as long as the compression stroke. Compression is limited because you cannot make it too hot, the gas fuel mixture, and then that limits the expansion. So this red point here, point 4, is the stuff you throw away. Out into the environment it goes. And there's what is called the Atkinson engine, which does a clever play having different compression and expansion strokes. How is it happening? When you draw air in, right, then you close the valve and you push back. In the Otto engine. In the Atkinson engine, you draw the air in all the way from here to here, and then you keep the valve open as the piston goes back, and then here you close the valve. And then you start compressing. So you have a short compression stroke, and then you have a long expansion stroke. And that brings your end point, after expansion down to here, low temperature, low pressure, you get more work out. The extra work you get out is this gray area in the plot. So it's very clever, and the Atkinson engine itself is old, but it was a very complicated business with lots of pistons and rods and things moving. But nowadays, because you can control valves electronically on, off, right, so there's nothing called a Nockenwelle anymore. For those who remember what that is. You can do very well, you can play very well with your valve timing, and you get this extra work out. And this is why you have Atkinson engines, in particular in hybrid cars. In hybrid cars, they have a low power density because they have this longer expansion stroke, so the engine itself is bigger, so the power density is smaller, the engine is bigger. But you can put a small engine in a hybrid electric vehicle, you run the engine at optimal conditions, and you use the electric motor to really propel the car. Right? So pretty much, according to Wikipedia at least, most hybrid cars use Atkinson engines, not the classical Otto engine. And why is that? Well, you reduce entropy generation and you do more work. Okay? This is what I say, entropy generation. So I will skip everything that has to do with the steam engine and the cooling cycle, and we go to air engines, by the way. I had the air engine on the poster, so I have to talk about this. And it's quite interesting. Similar idea. What is an air engine? So here's a very, very, very schematic air engine, right? What you have is the engine itself. You put in the fuel and you burn it. You provide energy by the fuel, so it's really like heat. And what you have, so you sit there in your seat next to the wing and you look out and you see the engine. This is what you see. You see mass flowing into the engine, and that mass comes with the velocity of the airplane, VA, right? So the airplane flies and scoops up air that is in front of the engine, and this has an air temperature outside. And then whatever happens in the engine, what you do is you expel faster and hotter gas. Right? So you take the gas, do something with it, but in the end you are back at the same pressure, but different velocity and different temperature. And if you look at the first law for this is now an open system, so we have to take this first law for open systems that we have before, mass, just one mass flow, and this is a difference in enthalpies, this quantity that arose, different in kinetic energies, and this is the fuel. So if you sit there in the plane, you look at this, you say, oh, what happens to the energy that comes with my fuel or this heat? Well, you use it to accelerate and you use it to heat. Okay? You're not interested really in heating the air, you're interested in acceleration, because what you really want is thrust, which is a force that pushes the plane, and propulsive power, which is the work done by the force to propel the plane. Well, the thrust, the force, is just Newton's law. The change of momentum is the mass flow times the change in velocity, in fact, between what comes in and what comes out. And the propulsive force is the velocity of the airplane times the force. Force times velocity is power. Okay? So you see, if you write down the first law in this form, it means nothing in terms for the propulsive power. The propulsive power does not really show up here, right? So this is because this is a wrong frame of reference. You sit in the airplane, you look out, you see what happens. The air is accelerated and heated. But where do I see that the airplane is actually propelled? Hello? Yes. Well, you stand on the ground, you see the airplane, and you understand very well that it is propelled, because you know there is friction acting on the wings, and if the airplane flies, there is a force acting on the plane that keeps it up there. So for us here on the ground, looking up, what do we see? We see air at rest in front of the airplane, right? And then the airplane flies by, and we see air expelled here with the relative velocity between the airplane and the VE, which is VE was the velocity with which the combustion product leaves the engine in the frame of reference of the airplane. But now we're on the ground, so we see it slow, right? And the air in front is hot. So what we see here is just by a change of reference, we can rewrite the first law, and it's just the same first law as this. All I did is combining these velocity expressions, these kinetic energy expressions, into the propulsive power and something which is, in fact, the kinetic energy of the outflow. So what you do is we have the airplane flying, and we see the airplane, it flies, we understand there's a force acting on it, and then we see what changes. What changes is this airplane spits out hot, accelerated air. Well, the air is hot, it will equilibrate, the expulsed air is hot, it will equilibrate with the surrounding air up there. Entropy generation, right? It's a temperature difference driving the equilibration, and we do nothing to harvest. Well, what could we really do, right? You can't get an engine that uses the hot air as it equilibrates with the outside. And the gas is hot, is fast, so you just have a flow of air that then in friction slows down, right? So you have entropy generation outside the engine, because your air is hot and your air is fast. And what you want is, and you see that here very well, the energy from the fuel, provided as heat, is split into the propulsive power. This is what you want. The kinetic energy of the exhaust here, which you just saw away, external entropy generation, and the heating of the air that you saw away. So these two contributions, the QH, the heating energy, the heating of the gas going through the engine, and the kinetic energy of the exhaust is just loss. You don't see it if you just look at the engine, that this is an irreversible loss. It happens outside the engine. So whenever you look at your system, you have to be very careful in evaluating, because some of the entropy generation associated with your system might be outside. There's stuff like friction, etc., inside your engine. But also there's stuff happening outside. You have to account for it. Right? So now what can we do to get the propulsive power we need to fly that airplane, to bring me here, for instance, and reducing these guys? The kinetic energy, you see, is the mass flow times the velocity difference, and the heating energy, just the energy to heat that air, is the mass flow times the enthalpy difference. Well, we need the thrust, we need the velocity. So what you can do is to reduce the velocity at the turbine exit and increase the mass flow. Because the kinetic energy that we saw away is linear in the mass flow, but quadratic in this velocity difference. So if you make the velocity difference smaller and the mass flow larger, we keep the propulsive power, but we reduce the kinetic energy of the outflow. Okay? So we want engines with large mass flow and small velocity difference. And how this is done, we see here, this is the high bypass turbofan engine. So what you do is you do not just use a compressor and a combustor and a turbine, which just drives the compressor, and then a nozzle to accelerate the flow out of the engine, but you attach a second turbine that drives this big fan, and the big fan pushes lots and lots of air to the outside of the core. This is the bypass, right? So some air runs through the engine in the middle, and this air is heated, comes out hot, and all that. And then a much larger amount of air runs through the bypass, mildly accelerated. So you have a large mass flow because you just take a big, wide cross-section, and then you don't have to accelerate the flow that much. Right? So you make a large mass flow, small velocity difference by building this bypass. And without much detail, here is a picture of the thermal efficiency, which is the propulsive power over the heat of the fuel as a function of the turbine inlet temperature. So in your engine, what you do, the combustion is here in the middle. This is where you burn, right? It's similar to the car engine. You first compress in a compressor. here, and then you have compressed air. You make it hot by burning the fuel, and then you expand it and use that extra energy that is there because the fuel is so hot. And the hottest part in the engine, therefore, is here, at the end of the combustion, the so-called turbine inlet temperature. It's something you can control. More fuel, more hot. Oops, that's interesting. So what we have here is the thermal efficiency as a function of the turbine inlet temperature. Oops, go back, please, would you? Right? This is turbine inlet temperature. This is the bypass ratio, the amount of mass that runs through. And what you see here is that for a given bypass ratio, there's an optimum efficiency for certain turbine inlet temperatures. And what you maybe see is that this maximum moves over here. So if you have a higher bypass ratio, your turbine inlet temperature, your optimum turbine inlet temperature, where the efficiency is best, is also growing. Or you can see it the other way around. If you can manage to grow your turbine inlet temperature to make it larger and make the bypass larger, you go to higher and higher efficiencies. And this is what people do. So you can, at 1500 degrees, right, your turbine blades are made of fancy alloys, but still at 1500 degrees, these guys would get weak and they would brittle and they would fly out. So you have fancy systems that cool the turbine blades from within. So they take cold air from the outside, push it through the blades into the flow so that the blades themselves stay cool. And that way you can increase the turbine inlet temperature. And that means for efficient operation, then you need large bypass ratios. So I always say that the best way to follow up with the development of engines is to watch James Bond movies, because in every James Bond movie there's a scene where a plane takes off because it goes to the Bermudas or somewhere else. Maybe not so much in the last ones, because now everyone flies. But those from the 60s, for sure, everyone was not flying, but James Bond was, and he was going to Bermudas. So you see a plane, and watch those movies again, you will love it. So there's always a cloud of dirt coming out of the engines, first of all, right? Lots of soot, black smoke, so these engines were dirty. And you look at the planes, the engines are very small. And now you go to the airport, because everyone flies, right? You fly, you see how big the engines are. And what you really see is the casing, the outside, the bypass, and the big fan in front. You don't see much of the interior. Here is for comparison, this is me in vacation outfit, obviously. No, this is in fact a fantastic place to visit. This is north of Seattle, the Boeing factory, where they built the 787 and other things in what they claim is by volume the biggest building on the planet. And you take a tour and you walk up on the very top, just under the ceiling, and you look down and you see these little Lego people building little tiny planes. It's really, really big. Anyways, but this is, I had to stand there just for giving you an idea of the size, right? But the idea of the big bypass is to reduce external entropy generation, which improves efficiency, okay? Here you see a very lovely picture of the bypass, right? So you see all this is bypass, if you see this, and this is the outlet of the nozzle that, for the air that comes through the turbine. So the cross-section for this is much, much bigger. There must be noise reasons for the wiggles here, noise reduction, stuff like that. I'm not too sure, yeah? But lovely picture, somewhere from the internet. So still we haven't said what entropy is, and we will not say for a little bit, and we will skip this section on property relations, which is also extremely cool, thermodynamics, which is just using multivariable calculus and Legendre transforms to explore the Gibbs equation, right? Which after all is just a differential form, which has the beauty that you can be used to relate things that you cannot measure to things you can measure, but we have no time for that, really. Let's talk about equilibrium. Right? So let's talk a bit more about the question of how the system, or what is the, not how the system approaches equilibrium, not yet. What is the equilibrium that we actually find? Right? We said equilibrium is a state of maximum entropy. But maximum entropy, of course, subject to constraints, because we always will constrain our systems. We will put a certain mass in there, we might shield it from the outside, and it will just be, so there will be no work, no heat exchange, so the energy will stay constant. So these constraints must be accounted for. And so if you look at the isolated system, for instance, here's our first law: the energy does not change over time. It's an isolated system, right? We do not put anything in or out. And I should have written the mass conservation as well. Here's our entropy generation, our second law. The entropy changes because there will be entropy generation until we reach equilibrium. So in equilibrium we will reach a maximum because we will grow all the time. But it's a constrained maximum because we prescribe the total mass as the integral over density, say. We prescribe the total energy as the integral over all the local thermal, kinetic, and potential energies. And we prescribe maybe the momentum as the integral over the local momenta, right? Just elements in the system might move. We look at a system where the overall momentum of the system is zero. That is, we look in a frame. We look at it in a frame where there is no momentum. The system itself is not moving. Stuff inside might move at the beginning, but the overall system is not moving. Right? So to find the maximum of entropy under constraints, we have to use Lagrange multipliers. Right? So this is thermodynamics is the perfect field to play with Lagrange multipliers. So if you teach mass, I can only encourage you to use examples from thermodynamics. Right? So we have to maximize entropy under constraints. We use Lagrange multipliers, and I will just tell you briefly what we find. We will find that the temperature is homogeneous and inverse to the energy Lagrange multiplier. But because the Lagrange multiplier is just one multiplier, right? So the temperature might be allowed in this evaluation because everything was integrals. We allowed inhomogeneous temperatures. But what we find from maximizing entropy under constraint is that the temperature is the inverse Lagrange multiplier. The Lagrange multiplier is just one constant. Therefore, the temperature is homogeneous. No surprise, right? We would expect that because we said, oh, temperature is equilibrating. That was our first example. We expect that everything comes to rest when the whole system is at rest. Yes, it must be. Friction destroys all motion and the velocity will vanish. That's the second Lagrange multiplier, right? So again, the Lagrange multiplier is just one constant. All the velocities are equal to the Lagrange multiplier, but the average of the velocities is the total momentum is zero. But for density, there's a leftover. That is interesting. So there's a Lagrange multiplier, but for density, there's a temperature, which is a constant. But here the gamma now is the acceleration in the gravitational field. And this is equal to what we call G, the Gibbs free energy, which is energy and entropy and pressure all combined. This comes out. This is what happens. Okay, so if we look at this, we see the first example of a competition. We will formalize it in a second, between energy and entropy. Right? So energy obviously plays a role here. This is gravitation, potential energy, and we have thermal energy here showing up as well. We have entropy showing up. So there's something happening. And to get something out here, this is the density Lagrange multiplier. So this should give us information about density, and if you evaluate it, say, for the ideal gas, where we know what the entropy is as a function of temperature and volume, you will not recall this equation in this form, but we used it before. We used the Gibbs equation and we integrated it. We know what entropy is. We know what enthalpy is. We find this expression. An exponential decay of density with height, which is affected by gamma, which is the gravitational acceleration, and which is affected by the temperature. If you do the same for an incompressible liquid, where the entropy is not dependent on energy, on temperature, on density, then you find something much easier, which you know it's hydrostatic pressure law. So this is pure energy, just the weight of the overlaying layers of liquid pushing the layers below. But here in the barometric formula, there is something more happening because the temperature is showing up. And the temperature comes in through the entropy. And this is where an entropic effect, entropy wants to, we will see that in a little bit, entropy wants to distribute the gas all over the accessible volume, and gravitation wants to pull it all down, right? So there's counteracting effects that negotiate some kind of agreement. And we can see that a little bit better if we look at systems which are not isolated but have prescribed controlled temperature and pressure for the boundaries. So then our first law, energy and potential energy, and here's heat exchange. We allow heat exchange. We prescribe the temperature of the boundary. That might mean heat exchange. We control the pressure on the boundary. That might mean a change of volume. So this is just the first law again with the prescribed boundary pressure. The second law with the prescribed temperature. And again, we combine the two by eliminating the heat. And what you find is not that the entropy becomes a maximum, but what you see is that this combination, enthalpy minus temperature times entropy, will go to a minimum. Okay? So things become interesting. And so here we see that a bit clearer, that there is this competition that I just mentioned. And you see, how can you go to a minimum if you have two contributions? Well, it depends. See, if you have small temperature, this second term will not matter much. So then you can get to a minimum when you make your energy contribution, in this case the enthalpy, really small. Right? So for small temperature, entropy effect doesn't matter much, and you go to an equilibrium with small energy. For large temperature, the equilibrium energy, the second term is much, much bigger, maybe, than the first term. So with this minus sign, the equilibrium goes to the state of large entropy, right? So you have a large entropy, and you don't matter, energy doesn't matter much, right? So there's this temperature that controls how important for the actual equilibrium state is the energetic or the entropic influence, right? So if you look at the barometric formula again, and here I spelled out the gas constant, in fact, is a universal gas constant over the molecular weight of the gas. So we can also consider what happens to heavy or light gases. So for small temperatures, the entropic effect is little. And you see, if the temperature is small, the exponent is really large, which means all the mass is pulled towards the bottom, to the ground. And you have the gas accumulating. We have not built in condensation in here, but it would fall to the ground, or would want to fall to the ground. And the same is if gamma is large. If you have a heavy planet with a large gravitational field, then the gas will be pulled to the ground. If you have, however, a light planet, a small gamma, or a hot planet, large temperature, then you have an almost flat density profile, which essentially means that the gas goes off the planet and goes away. So you look at Mercury, which is close to the sun, it's very hot, it's a small planet, it's very light, it has no atmosphere. You go to Jupiter, it's far away from the sun, it's cold, it's very heavy, it's all gas pulled together. Okay? And then you guys probably once in a while you give a helium-filled balloon as a present. Yes? Where does the helium come from? From a bottle. Very good, Manuel. The question is, where was the bottle filled? Here's an interesting thing. You see because here's the M. If your molecular weight is small, you have a more flatter density profile and the gas can escape. What is the most common element in the universe? Yes, hydrogen. What is the next most common element then? Helium, exactly. So why is there no helium in air? Because it is all gone away because it's too light and entropy wins. Entropy wants to distribute, we will see soon why. Entropy wants to distribute the gas as much as it can. Energy wants to keep it together on the ground. So most of the helium, I understand, comes from natural gas, which you take out of the ground, and that natural gas was formed long ago, when there was much more helium in the atmosphere than is now. Okay? Helium is difficult to get by. There's very, very little helium in air, very little. Okay? And the United States, they have some collection place where they have it, but it's getting difficult. And what do we do with the helium? We find no better use than putting a balloon in. Ancient helium. Liquid vapor phase equilibrium is a similar thing where you see this at low temperature, energy wins. There is an attractive force between particles, right? Particles want to stay together. So energetic minimum is particles stay together and form a liquid or solid. Entropic state is distribution all over the place. So at low temperature, entropic contribution doesn't matter. The energy wins, everything becomes a liquid. At high temperature, entropy wins, everything tries to fill as big a volume as is possible, and you have a vapor. Interesting is the temperature in between, and for sake of time, I will not go there probably. In between, energy and entropy negotiate an agreement for equilibrium, which is, well, we find a minimum where some of us is in liquid and some of us is in vapor state, and we're fine. Okay, and this is the liquid vapor equilibrium. And so what happens here is that the Gibbs free energy, enthalpy minus temperature times entropy, must be a minimum. And if you think about a system where you have a liquid and a vapor, the total Gibbs free energy is the mass of the vapor times the enthalpy Gibbs free energy, small g, of the vapor, and the mass of the liquid, which is the total mass minus the mass of the vapor, times the Gibbs free energy of the liquid. So you have the coexistence if these two Gibbs free energies are the same. And this gives a relation between temperature and pressure, in fact. You have two functions of temperature and pressure, they must be the same. They cannot be so for all values of the pressure if you prescribe a temperature, but only for a particular pressure, which is called the saturation pressure. Okay? So low temperature liquid, high temperature vapor, and then there is a state in between, where you have coexistence of both in a particular pressure, saturation pressure. This is if your temperature is 100 degrees, your saturation pressure is 1 atmosphere. This is the temperature at which this is the pressure at which water boils for a given temperature. Okay? And I just had to throw this in on the side. What is with ice? Ice is this weird. Water is this weird thing anyways. So there is a saturation pressure also for the coexistence of liquid and solid. That's the melting pressure if we talk about ice and water, liquid water. And water is this weird substance which swims on it, where the solid swims on the liquid, which is very seldom, and one can show, and I will not show here, that this has to do then with the fact that the melting curve has a negative slope. And I just, since I have your attention, I have to mention that. So this means at higher pressure, ice melts at lower temperature. You have ice of 10 degrees, you squeeze it hard, it starts to melt. You guys skate? No Canadians here? No? You guys skate? Whoever was in his life or her life skating, ice skating? Oh, good. It was slippery, wasn't it? So I just want to tell you that ice is slippery not because the ice is melting under your skate. It's something people think, and it might be something to think because that melting curve has a negative slope, so that indeed, if you squeeze on the ice, it will melt at lower temperature, although it is below freezing temperature. But ice is just slippery. You do the math, there's a little assignment here. If you watch the video later, you can think about it. The pressure would by far not be enough. It would just be a fraction of a degree that you can lower the melting temperature under your skate. And there's also a very interesting thing. Water cannot be liquid below minus 20-some, 21, 23 or 30 degrees. But you can no problem skate at minus 30 when there is no liquid form of water possible at whatever pressure. I talk to Canadians. They skate whenever. So ice is slippery. There's a molecular layer of liquids. You create friction as you slide. That might melt some. And there's a very small contribution from pressure melting. So water, you would think, is the most important of the substances for us, but people understand very little. So this is still open to discussion. You look into the literature every couple of years. So 5 years ago, 6 years ago, it was ice simply is slippery. Now it's ice is slippery, but there's a lot of frictional heating. So it's very difficult, apparently, to find out. Glaciers flow due to plastic deformation. And now finally, what is entropy? Manuel was waiting. How can we understand this desire of nature to make entropy larger? Oh, but first, what is entropy? You see, so far we haven't had to bother. It's a quantity that arises when we construct an inequality that describes the trend to equilibrium. We look at it from all sides, we squeeze it, we push it, and we come out with everything we need to know. But one thing, what actually makes this happen? Right? So I said this before, it's easy to observe the second law in the kitchen, but not the first. But of course, it is interesting to understand a bit better what entropy is. And for that, we go to the microscopic viewpoint. And we do this in an extremely simple way. Okay? And just so that we get the idea and not the details. Right? So I said microscopic, so we have to go now and look at what actually happens if you say, take a container filled with a gas. Right? So from the microscopic viewpoint, what we did so far, we describe it by something like temperature, pressures, mass densities, velocities, or even the total mass, the total volume, the total energy of the system. Right? So we can go local, assuming the gas behaves like a continuum, and then we look at local values of the fields, or we look at the overall. But when we go microscopic, essentially what we have to do is we go inside and we look at the location and the momentum of all atoms in the system. And there are many, as you know, a huge number, 10 to the 23 and counting. And I just said location and momentum, I should say location, momentum, and quantum state, right? So an atom or a molecule is something which is quite complicated in itself. And what happens if you look at our gas is that all these particles are running around because they carry energy, right? For a gas, a simple gas, the energy is just the kinetic energy of the microscopic motion. You make it hotter, the particles fly fast. Right? So a microstate is locational momentum of all atoms. For us now, ignore that quantum bit. And the microstate is changing all the time. Particles flying around, colliding with each other, colliding with the boundaries. Different microstates at every split second. No matter how small the split second is, you have different microstates at all the time. So for one macrostate, say a gas in a container at a given temperature, we just need the mass, the volume of the container, and the temperature, and information about the type of gas, and we have complete description of what happens inside from the macroscopic viewpoint. But inside are all these particles flying around and changing their microstates all the time. So there are lots of microstates that describe the same macroscopic state. We do not see the change of microstate. This is why it's called micro. We are macroscopic, we ourselves. So our perception is macroscopic. We see the macroscopic state, but we have to understand there's a lot of stuff happening. Or in a solid, all these atoms, they're not changing their location within the, say, the crystal lattice, but they're moving all the time, they're vibrating, there's waves going through this. Lots of complication, lots of microstate, but maybe the same microstate. Okay, so now why does a gas fill the volume? Here's a simple example. The gas is 2D, it's 9 particles in a box of, or in a volume of 81 locations. So it's even, the particles hop from one location to the other. And why do they hop? Because they have thermal motion. They hop. In real life, or we could go to kinetic theory, which Manuel and I love, and have particles fly and collide and all that. And that would be how the particles transfer. But just looking at the different microstates that are possible for this particular gas, where the particles can be in either one of these 81 boxes, locations. Well, we count microstates, right? So it's a number of now I'm confusing myself. Is this right? That capital N as a particle is small n as a location, or is it vice versa? It should be right, I hope. We count the distribution. This is from my book, it should be right. It's black and white, right? So we count how we can distribute all these particles of all these locations. And the formula is right, but yeah, no, this should be right. So the particles move from box to box. And now we say, okay, all these microstates have the same probability. There's not a distinguished microstate that is assumed more often. How would it? I mean, of course, it depends on some correlations. Maybe there are correlations between how the particles fly, then there would be some difficulties. So we assume some way of molecular chaos, but then all the microstates have the same probability, each individual one. So even for this simple set, the total number of microstates is 10 to the 11th. That's a lot of microstates, so you don't want to try it out, right? So there would be states where all 9 particles would be up in the box here, in the 9 by 9 box, or all would be here in a row. Compared to that, the number of microstates where the particles are just in 1/3 of the volume is 10 to the 6th. So it's several orders of magnitude between. Right? So that's the thing. Most of the microstates look more or less like a homogeneous state. There are fluctuations. You will not always have, this is maybe not the best picture, right? Because you have one particle in each 9 by 9 box, 3 by 3 box. But more or less it will always look like this, and very seldom like all the particles will be just in one corner. You would not expect the air in this room suddenly to be over there in the bookshelf. Right? No. Will not happen. Most of the states, just counting, shows that most of the states look more or less homogeneous.
Is it really random where the positions of the
It's not really random. Of course, you could go and that's a complicated question with a non-easy answer. The particles, of course, you have Newtonian mechanics between the particles. So Martin Frank, he asked me, "Oh, will you tell about the origin of irreversibility in kinetic theory?" It's a very difficult topic. It's difficult to pinpoint. You start with Newtonian mechanics and end up with disorder and chaos. So there are some assumptions that you put in. For sure, it's a non-correlation of the initial conditions. You cannot even control the initial conditions, right? So if the initial conditions are random, then the later outcome is more or less random. But this is just very basic assumptions, okay? So simplified, boiled down. So Boltzmann, from his famous Boltzmann equation, he found that the macrostates with more microstates have larger entropy. So there's a link between the number of microstates that you have for a given macrostate and the entropy of the macroscopic state. And this is just a logarithm of the number of microstates times a constant. That constant is called the Boltzmann constant and something like the gas constant for particles. Now, if we accept this, and we accept this simple example as something meaningful, and we accept that the number of locations is proportional to the volume, with a little bit of mass, we find the entropy difference between two states, two macrostates, just being the logarithm of the ratio of volumes. This is something that we found before from the Gibbs equation and the ideal gas equation, just integrating it. Okay? So, just using this simple example, we find the principal behavior of the ideal gas. Yeah? And again, what we see, this pushing or this distribution of the gas over the whole volume, that's what I said before when we talked vapor, when we talked atmospheres. The entropy wants to distribute across everything. It wants to fill the volume as much as it can. So consider this gas here, and molecules, originally confined in a small volume here. And then we let go of the constraint, which is we take the wall away. What we will see mostly is this. So the gas, essentially assuming chaotic or enough random behavior, the gas explores all accessible volumes, which is all accessible microstates. And the ratio of the number of microstates, just looking at this coming from Boltzmann's definition, the number of microstates for the system without walls as compared for the system with walls, where the gas is confined, is the volume ratio to the power of n, where n is the number of particles. Right? And n is 10 to the 23 for a macroscopic system. So this ratio essentially is ridiculously large, no matter how the ratio of the volumes is. So this means there are so much more microstates in the larger volume that we will see the gas in the larger volume. Or you can ask, still assuming random behavior, what is the probability to find all gas particles in the initial volume when they can access a larger volume? It's just the inverse of this number, of course. And it's so really small that we will never observe it. Right? So there was much discussion at the time of Boltzmann about this. And essentially Boltzmann's argument was that, it is not excluded that the system will go back into this, it is just so unlikely that we will never see it. You can wait forever, minus 1 day, and then you might not see it. You have to wait 23 hours longer. It is very, very unlikely that the system goes back just because of the, not random behavior, but just the evolution of the gas. It will be like this. You can just do very simple models, and you will see, even if you have deterministic behavior, after a while you will see the gas distributed. Ideal gas entropy. We found this before from the integration of the Gibbs equation, right? And we just found this volume term from this very simple model, saying, oh, this gas distributes. And too bad. In the things I ignored, stepped over, using the multivariable calculus to explore the Gibbs equation, one can find, just from the Gibbs equation, some Legendre transforms, one can find relations between the energy and the entropy here. So this is a change of energy with volume, there's a change of entropy with volume, there's the pressure, the temperature, just the Gibbs equation, essentially behind this. Since for an ideal gas, the energy is not dependent on volume, this is because it doesn't matter for the ideal gas how far the particles are apart. They only notice each other when they're really close for a collision, but as they fly between collisions, they don't notice the presence of other particles, and therefore there is no matter whether the particles are on average closer together or not, no influence on the energy, no potential energy between the particles unless they collide. So the energy is independent of the volume, so this left-hand side vanishes, and this means that the pressure is just the derivative of entropy with the volume times the temperature, and this gives us the ideal gas law. So you find the ideal gas law from this simple argument. The ideal gas pressure is just because of the entropic desire to fill an even larger volume and push the walls away to increase the entropy to have a even larger volume. Yeah? So it is the entropic desire of distribution over a larger volume that makes the pressure in ideal gas. Right? In a liquid, it's just the weight. But in a gas, it is the desire to push. All this is a bit even better to see maybe in mixtures. So down here on the bottom there's a picture of what happens in mixing. We have 1, 2, 3 new different components, unmixed, all under the same pressure and the same temperature, enclosed in compartments. And now we open the compartments to each other and we wait, just like we waited for our coffee and our milk, and after a while we have mixture everywhere. Okay? So now we can again do a very simple assumption, ideal mixtures. So we have n alpha particles of each type, and we just have as many locations for the particles as we have particles in summer. So n is the total number of particles. It's also the number of spots the particles can have. It's not like a gas where you have empty spots in between. You have just as many spots. And again, you can go and compute the number of microstates, and there's then just one microstate, if you assume that the particles are indistinguishable, that describes the initial state, right? Because all the one particles have to be in this box. There's just one microstate. Each spot is filled with a one particle. But for the mixture, there are many more spots. And again, we use Boltzmann's definition. We find the entropy of mixing, the difference between the entropy of the mixed state, just based on the number of microstates, and the initial state. We find this entropy of mixing. X is what we call the mole fraction, just the ratio of particle number over total particle number. It's the particle fraction or mole fraction. And so we find the overall entropy of mixing for the system. And there's a minus sign, but of course the mole fraction is negative, so this is positive. So as we let the system go from unmixed, we remove the barriers, we let it mix, the entropy grows until it is at a maximum of the entropy, which is a perfectly mixed state. So then we go to the kitchen again and we mix wine with water. And we know quite well this works. And then we make a vinaigrette and try to mix oil with water. And it doesn't work. The oil separates, swims on top. So I just said ideal mixture will mix, right? There's an increase in mixing. So what's the difference here? Wine and water, oil and water. There are forces, there are energies, because it's not the entropy that goes to maximum, it is the Gibbs free energy, which is enthalpy minus temperature times entropy, which goes to a minimum. When wine is mixing with water, there's no energetic effects. Water and wine particles are perfectly happy to be neighbors, and so there's no entropic energetic contribution. Entropy wins, and you observe the mixed state. However, oil and water, they don't like each other. Oil wants to stick to oil, and water wants to stick to water. So there would be a large energy required to form pairs of neighbors of liquid and of oil and water. And that energy is so large that there's a much smaller energy when they are separated, and this is why you see the separation. So the more or less unmixed state. Salt solutions is another interesting similar problem. So why has a salt solution a higher boiling temperature than water, right? You put your pot of water on the stove, it's 1 bar outside, it starts to boil. When you put a thermometer in, it starts to boil at 100 degrees. On the other stove, you put on salt water, you throw salt in, same pressure outside, it starts to boil at 101 degrees. So why is that? It's getting more interesting, huh? So why does the water evaporate after all? Well, it wants to increase its entropy, right? The vapor has a bigger entropy, fills a bigger volume, so the water wants to evaporate to fill a bigger volume. The salt, however, it will not evaporate. It's not at 100 degrees or anything. It wants to stay in the liquid. And it wants to have a big volume to swim about because that is better for its entropy. So the salt would like to have a large water volume to have high entropy. The water would want to evaporate to have a higher entropy. So it's two entropic effects fighting against each other. And you have it's more difficult for the water to evaporate because the salt keeps it back. Do I have that written down? Same thing, right? Energy minus entropy, but this is, oops. Why does ice melt when salt added? Same thing. The salt would want to have a volume to swim in. So the ice, as the salt, is perfectly happy in the crystal, but there's a lower energy and a bigger entropy when it dissociates into ions and swims in the liquid water. So it melts some water for itself to be in a lower state together with the water. So this is why you put salt on ice in winter, you melt it. It's the entropic desire to swim in a larger and larger volume. Right? So this brings us to this, the power of osmosis. The same thing, right? It's a similar thing. So on one side you put a pure solvent, say water. On the other side you put a solution where X is the amount of stuff dissolved, say salt solution, salt water. And in here we have a membrane which allows only the solvent to pass through. The salt cannot go to the left. The salt will stay on the right, but the water can go to the left, to the right. The water can go anyway. So now what happens to the system depends on the pressures we put in on both systems. And if you want to have a steady, a fixed state where nothing changes, we have to find out how strong we have to push on both sides of the container. Right? And the difference in the pressures is what we call the osmotic pressure. So in fact, because the salt, the stuff dissolved in the solution, wants to have a larger volume, it wants to draw liquid from the solvent to the other side, across that membrane. And you have to stop drawing it by pushing harder. So if you push with a pressure of 1 bar on the left, and you have just seawater on the right, you have to push with a pressure of 28 bar to keep fresh water from crossing the membrane to expand the volume that the salt can fill. And here's an equation for it, for the osmotic pressure, right? It has to do with the salt concentration, the mole fraction of the salt, and you see the osmotic pressure is larger when the fraction gets smaller. You can see this? Gummy bears. There was a news item the other day, a guy died because he drank too much water. Did you read that? Yes. A couple of days ago, a marathon guy. He drank too much. If you are abandoned at sea on a float, you can die of drinking seawater. Both two sides of the same coin. It's osmosis. So our body has an osmotic pressure of about 7 bar, I think 7.7 bar. Our cells are filled not with water, but with salty water. There's stuff swimming in it. So if we drink too much salt water, we have all this salt outside our cells, and the salt in that salt water wants to have a bigger volume to swim in, so it draws water out of the cells. And our cells crumble like raisins, right? A raisin is a perfect example. There's sugar in there. You take a raisin, you put it into fresh water, it will grow, because the sugar's desire to have a larger volume will draw water back into the raisin. If you drink too much fresh water, then that fresh water will enter our cells and the cells will make pop. So either way, it's an unhealthy endeavor. So you see these two gummy bears. One is in a salt solution and one is not. So which one is in a salt solution? Huh? To the right, the small one. Because the salt keeps liquid with it, whereas on the left, the sugar in the bear draws all this water, maybe the polymer, and this guy can grow. Okay, so there's strong forces in osmosis. Why is this on battery? That's interesting. Change of entropy can be related to work. So this is again combining the first and second law. I will not go into the detail, but I would like to state it. So if you want to separate, you have to work against the desire for mixing, which is the entropy of mixing. So the work that you have to put in for separation is at least the entropy of mixing plus anything irreversible in your process, right? Which you will always have. So some basic work, the minimum work is the entropy of is to overcome the entropy of mixing, but then you have entropy generation. It's just a combined first and second law again. You can do it vice versa. You can obtain work from mixing, and that work is related to the entropy of mixing minus whatever entropy you generate. Okay, so the principal way to do this is a reversible mixing device. It's a bit unclear here how it works. The next slide will give an example. So what you do is you take fresh water in, you take some rather salty water in, we call it brine here in this picture, and something happens inside, you get work out, and you throw out the mixture of the two flows by getting work out. So how can this be done? Here is osmotic power plant. So this is, osmotic power is really just the desire to mix, and we harvest it. And what we have here is fresh water coming in, and we have seawater coming in, and the seawater is pressurized to a higher pressure, and then fresh water and seawater are brought in contact at this membrane where the fresh water can pass through. Because the salt wants to have this larger volume to swim in, it draws fresh water, although the salt pressure is higher than the freshwater pressure. So there is fresh water drawn against the pressure gradient just by the osmotic force. So as a result, the pressure doesn't change much in this salty flow, but the amount of water in the salty flow changes. So what comes in here is a small flow, small salty flow at elevated pressure. What comes out is a large flow of salty water at elevated pressure. Now, elevated pressure means you can expand it to the outside environment, get work out. So we split it in two parts. One part is needed for the increase of the pressure of the incoming water, which is environmental pressure. And the other part is running through a turbine, we get power out. So this can be done. Problem is that there are lots of irreversibilities, I told you. The irreversibilities are what costs us the flow through the membrane, right? You squeeze the water through tiny pores. Of course, there's a loss. A pressure exchanger, which reduces the pressure of one flow and increases the pressure of the other, is not a reversible system, of course. There are losses, friction losses, filling and emptying losses. A turbine is not perfect. So there's lots of irreversibilities within the system. So there was a plant operating in Norway. They closed it a year or two ago. It was a small plant. They say the membranes are still not there. So you need very good membranes with very little flow resistance that makes this work. Another thing people talk about is sequestration of carbon dioxide, right? So you're interested in getting less carbon into air. If you look at the concentration of carbon dioxide in the air, it's 400 ppm, 400 parts per million, which is 0.04%, right? So it's very little. So if you look at the work for separation, the work for separation is the entropy of mixing. The entropy of mixing has to do with the logarithm. Do I have it somewhere? Come on. With the logarithm of the concentration. So if the concentration is small, then the entropy of mixing is large. So it's more difficult, you're not surprised, it's more difficult to separate a small amount of a large amount than separating, getting some stuff out of a large, where it's equal, right? If you have 100 1-cent and 100 2-cent coins, it's easy to find a 1-cent coin. If you have 198 2-cent coins and 2 1-cent coins, it's more difficult to find the 1-cent coin. In particular, because you have to sift through all the 200 coins, most likely to get the 1 penny coin. Whereas in the even distribution, you just need a very small amount of your coin mixture to find the coin you like. Right? So you have to process much smaller amount of substance. At any processing of substance is involved with running it through system, friction losses, etc. So if you have to run a large amount through your device, you have a lot of entropy generation just because of the mass. Right? So if you want to separate carbon dioxide from air, where the concentration is very small, you have to run a lot of air through your system to find the amount of carbon dioxide you want to put away. So what people therefore want to do is separation of the carbon dioxide from source. And here's an example for a steam power plant. What happens here is you take air in and you take an air separation unit and you take oxygen out. You separate the air into oxygen and the rest. The rest you don't care, you're interested in the oxygen. You mix it with some of the exhaust that comes out at the other end of the power plant. And then you have, instead of oxygen and nitrogen and whatever is in air, you have oxygen and carbon dioxide and water. And you run this through your engine, through your combustion system, your boiler, etc. So your exhaust is only carbon dioxide and water vapor. You burn carbohydrate fuel. And then the carbon dioxide can be easily taken out. You see, oxygen is 20% in air. Carbon dioxide, just in the environmental air, is 0.04%. So it's much easier to separate oxygen out and then use it this way, and then having carbon dioxide and water in the exhaust, you can split that easily. You just condense the water, essentially. Right? But no matter what you do, you have to pay for separation. You act against the desire of the gases to mix, which is you have to put work in. And that work is large, so 20%, 25% less power of a system where you separate the oxygen at source. So this will never fly. All plants that were in development are closed. They plant something in northeast Germany, and people force, so just a plan to try whether this works, and the people living there forced it to shut down, I believe. Well, you wouldn't want to have a lake of carbon dioxide below you. If there's a leak, that carbon dioxide is a heavy gas. It accumulates on the ground, pushes air away, and you breathe carbon dioxide. It's not most healthy thing. So it's expensive, difficult. People still talk about it. Gas solubility. It's another one of these smaller things that are interesting to mention. So that's the question. How much gas is dissolved in water when the gas pressure about the water is PV alpha? Say you have oxygen partial pressure, right? We have 1 bar outside. We have 21% oxygen in air, so the partial pressure of the oxygen is 0.21 bar. How much oxygen is dissolving in the liquid? That's a difficult question because all these ideal gas assumptions and mixing assumptions do not really work when it comes to water. Water is such a beast, right? Because of this polar nature of the water molecules. So whether water wants to be an oxygen or nitrogen neighbor or not is a question of, again, an interaction of energetic contribution and mixing contribution. Of course, there is an increase in entropy if some of the gas mixes into the water, but also you form neighborhood between oxygen particle and water particle, and they might not like each other. So this constant here that tells us X again is the concentration of gas alpha in the water depends on the pressure. The more you press, the more gas will be in the liquid. And a constant H alpha, temperature dependent, it's called Henry's constant, a function that is gas specific about and temperature dependent. So this constant grows with temperature, so there's less gas dissolved at higher T. It's just then nice to have a large entropy in the gas. I have some interesting things come out of this. So there's more oxygen in cold water. So this is why if you go to the Bermudas, you have wonderful clear water. Nothing lives in that water. You go to the Northern Sea, to the Ostsee, Baltic Sea, the Arctic Oceans, the water is all muddy because there's so much stuff living in it. And it lives there because there's so much oxygen. It's not a pure entropic effect. It's an interplay between entropy and energy. The constant here for nitrogen and oxygen is very small. For carbon dioxide, it's much bigger, which is something you experience every day if you have carbonated drinks. Right? There's carbon dioxide in there, and there's a lot of carbon dioxide dissolved in the liquid under the elevated pressure. So there's, of course, no air up here. This is carbon dioxide under elevated pressure. So there is gas dissolved in the bottle, in the liquid, in this Victoria Coke. And when you open the lid, the pressure goes down and less carbon dioxide wants to be dissolved, so you have bubbles forming. Now, if you guys like Guinness beer, you like Guinness? It's you don't, by definition, because it's impossible to get it in the Aachen supermarket. At least those I tried. Wrong city. It's interesting. The thing is this. I don't want to drink Guinness. Don't worry, because it's thermodynamically interesting. Here it comes. Here it comes. Guinness is nitrogenated. So there's nitrogen in Guinness beer. Okay, so if you go to an Irish pub, which you weirdly find everywhere in the world, they have a special tap system for pouring the beer into the glass, where they squeeze nitrogen into the beer. Okay, so there's some carbon dioxide in it, but also nitrogen. And when they started to put it into a bottle, they didn't know how to deal with the nitrogen, because here you see the constant for carbon dioxide is 1600, the constant for nitrogen is 85,000. So there's a big difference. So you cannot bring any nitrogen in this solution with a liquid, or not much. So they invented what they call the widget to get nitrogen into the can, and this is why I wanted to buy a can and bring it. So I went to Wikipedia instead. So if you buy, you can't do it, right? You're in Aachen, you can only find Belgian beer, which is probably very good beer. So they put this little plastic ball, which has teeny tiny holes, and when they fill the can, they put a drop of liquid nitrogen into that little plastic ball, and then they close the can, and the pressure is high. The nitrogen, of course, evaporates, but stays in that little ball because of the pressure, right? There's pressure force. There's no way it can go out. It's just pressure equilibration. There are tiny holes, the liquid cannot get in. And then when you open the can, you release the pressure, and then the nitrogen can go through these little holes that are in the ball, which you cannot see in this picture. And you have this fine foam in a bottle. Applied thermodynamics. One more, because it is so important. Something people don't know as well. Ammonia. Probably could call it one of the most important substances in the world. New number in Wikipedia, 1.4% of annual fossil fuel use is to produce ammonia. 1.4%. So that's a big deal, right? A big deal. It's used for fertilizer and explosives. 100 years ago, it was not available on a big scale. Which made wars maybe more peaceful, but farming more difficult, right? So we have a lot of nitrogen fertilizers, and if you look at the numbers, I just saw the numbers. Beginning of the 19th century, 90% of Americans worked in farming. 90%, 90, and now it's 2%. So I would call that a triumph of thermodynamics, because it works. Because what does a farmer need? Big equipment, right? tractors, threshers, all this stuff, and good fertilizer. And so, of course, the tractors, etc., that's thermodynamics right away because of the engine. But the ammonia for the fertilizers is quite important. And so this brings us just to mention chemical equilibrium, right? So we bring two substances that can react together, and they want to react, maybe, depends on the Gibbs free energy difference between the unreacted and the reacted state. Ammonia here is nitrogen, which you just take from air. Easy, right? 79% of air pretty much are nitrogen. Hydrogen, which is difficult to find unless you send a guy to the sun and take a scoop out. You have to make it, right? You have to make hydrogen. And this is where the fossil fuel use comes in. This hydrogen is made from natural gas. You just take methane, which is natural gas, CH4, and you do a reforming steps with water to produce hydrogen. They react to, so 4 molecules react to 2 molecules. This is what happens here. So we have no time, again, just scratching surfaces here and there about the minimum, but there's Le Chatelier's principle which says things very nicely. A change in one of the variables, like temperature, pressure, or concentration, that describe a system in equilibrium, produces a shift in the position of the equilibrium that counteracts the change. Think about this reaction. It's in the volume. You change the equilibrium by changing the pressure. You push on it. Right? Equilibrium, I should say that. If you burn a fuel, all the fuel is gone, right? It's consumed. Typically, in chemical reaction, you bring 2 reactants like here together. The final equilibrium is the reactants and the product, all together in different amounts. And you want to increase the amount of product and decrease the amount of reactants. But typically you have all. Only fuels are so extremely keen to react that the equilibrium is on the product side. The product being using up all the fuel. Right? So we take this mixture, reacting mixture, we squeeze on it, so we increase the pressure and we reduce the volume. Right? So Le Chatelier principle says, well, we decrease the volume, so the reaction would want to go to an equilibrium where the volume is naturally smaller. And the pressure smaller as well. The reaction can do that by going more to the product side, right? So if you have 4 gas particles, if you look at an ideal gas, it doesn't matter what type of particles you have, the pressure is proportional to the number of particles. If you have less particles, you reduce the pressure and the volume. Right? So if you squeeze on a reacting mixture where you have, like here, 4 particles going to 2, you have less. You move the system to the side where you have less particles, which is product side. So you can control, by setting temperatures and pressures, you can control your thermodynamic equilibrium, your reaction equilibrium. If you have an exothermal reaction, heat gets set free when you run the reaction, you get less product. In this case, this is an exothermal reaction, so if you run it at higher temperature, you produce less ammonia. So look at the numbers. If you go at standard outside, right? This is all for free. 1 bar, 300 Kelvin, which is 27 centigrade. You get 93% product, which is great, right? So you would want that. But these guys don't want to react. This is what made it so difficult and really a triumph of thermodynamics. These guys don't want to react. They prefer to be at nitrogen and hydrogen state, and not because the equilibrium is not on the product side. The equilibrium is very much on the product side. But you have to get there, and it's not always that things happen automatically. There's a metastable state where the 2 just stay together. It's the same as the Knallgas, the oxygen-hydrogen mixture. You need a spark to get it going, right? Because to get it going, you have to break the bonds that keep the molecules, nitrogen and hydrogen molecules, together. And for that, you need catalysts. So this is I just couldn't resist to throw it into this presentation. So you need a catalyst, which is something basic, iron, but that catalyst works only at high temperature. And then you suddenly, because of the second part, again, this is just negotiations between energy and entropy. That second part is 13% product at the high temperature that your catalysts need. So you have to squeeze hard to get to 30% of product, just because it's not that easy to get to an equilibrium, right? You have to use catalysts to break bonds, to overcome barriers that keep metastable states stable. This is a Haber-Bosch process. So this really changed our life more than you could imagine. Bosch was the industrial guy. Haber got the Nobel Prize for this, right? So one page of thermodynamics, a big page. 2 pages of thermodynamics. Incredibly. Fuel cells. Chemical reactions are irreversible typically. Why are they irreversible? We have no control, right? We put that spark into the hydrogen-oxygen mixture and it explodes. After we put the spark, we do nothing and it combusts. Right? So there's something uncontrolled about it. If we have no control, if we cannot stop the process at any time and it keeps going, this is an irreversible process. So there is, in a chemical reaction, just in burning of a fuel, there is irreversibility per se. Combustion, irreversibility. And why is it irreversible? Well, if you think about what chemical reactions are, it's just a reconfiguration of electron shells, if you like. So we do not control the motion of the electrons, so it's irreversible. Fuel cells try to control the path of electrons. So what you have in a fuel cell is a complicated thing. You have these electrolytes where the electrons cannot go through. On one side, use a catalyst to split the hydrogen into protons and electrons. And the protons go through the electrolytes. The electrolyte is an acid. And the electrons go through your device, say the engine of your car, the electric motor. And on the other side, you supply oxygen. The electrons arrive going through the outside. The hydrogen, the protons arrive coming from the electrolyte, then combine to water. So you have a controlled path of the electron. So you use the desire to react to control the path of the electron and to get work out of this, electric work in this case. Okay, so it's the same thing. The stuff wants to react, that desire is strong, let's make use of it and milk it. This is a way to milk it. The first fuel cell car is in production now, I believe, but the efficiency is still low. No time to go into the irreversible process, the activation loss, resistance, etc. Electrolyzers are the inverse. So the overall conversion, where you use an electrolyzer, an inverse fuel cell, to split, you have to act against the desire to be reacted. And you process the fuel to store it and you power it. It's very low, 25%. No, and Armin, I'm sorry, we will not talk about local equilibrium because time is up. Often it's said that entropy is a measure for disorder, right? You find an engineering textbook that says entropy, a measure for disorder, and then you try to read it and you can't understand what they mean. That's because they don't talk about microstates. So most microstates just appear disorderly to our eye, and therefore we say we might be inclined to talk about disorder here. A single microstate has no entropy, that's very sure. Entropy is something that describes a macroscopic system, not a microstate, not a current microstate. Entropy counts the number of accessible microstates for the macrostates that we consider, and only that is entropy. So a single microstate has no entropy. And here's a microstate of a bookshelf. The macrostate for that is all books are in the bookshelf. Right? So you can reorder the books as you like, but still they're all in the bookshelf, and you can count the microstates, how many ways you find to distribute your books. It's not that many. So this is a macrostate that has a small entropy. This appears orderly to us. You need thermal motion to drive the system through the microstates that it can access. I think I have the thermal motion here. It's the customers in the bookstore. So there's far more ways to distribute the books in big heaps all over the tables, right? I mean, I could let you loose on what is behind there, and I'm sure you find a way to make it look disorderly. Yeah. So it's not that disordered states are what you will observe. What you will observe is that what happens is that most microstates appear disorderly to us, but a single microstate has no entropy. It's just about what you allow or not allow to happen. As life goes on, we all work in the department of entropy. It falls apart. And what about life, right? So your religious life, obviously we are highly organized, right? We are not a heap of dust. So does it violate the second law? And the answer is no. Of course, we're not isolated. We live from the sun, as you all know. Everything that really happens on the planet is driven by the sun, the winds, the weather. Fossil fuels come from the sun. Uranium is baked by a previous sun. So everything comes from the sun. We are not isolated. And if you're not isolated, we bring in energy at high temperature. We discard energy at low temperature. It's no problem for us to lower our entropy. It's not that entropy cannot go down. An isolated system, entropy can only go. But in a non-isolated system, entropy can go down. Of course, it's just an equation, and there's a contribution. The entropy generation is positive. But if we just manage to provide and withdraw the proper amounts of energy in form of heat at different temperatures, we can shrink our entropy no matter. And of course, if you look at ourselves, we eat low entropy food, we discard high entropy waste, we sweat, right? This room. So we discard energy. Here, this is Q is negative for us as we sweat, as we give heat to the environment. It's tougher for us in a warm environment because it's more difficult to get rid of the entropy, to keep the entropy, and therefore the concentration low. Concentration high, entropy low, right? It's more organized. And that's it. Pretty much on time. So this was a wide circle all over entropy. We could only scratch here and there. I hope you understand. So as a challenge, you walk through beautiful Aachen, you walk through your life a day, and you watch out for entropy producing processes, or for processes where you have to reduce entropy. You make an effort. You will see it is pretty much everywhere. This is really all there is to it. Thank you. Yes.
So where exactly does this come into play, and what are
the principle of maximum entropy production states that this is a statement about the approach to equilibrium, which we now, because of time issues, completely ignored, right? But we looked at equilibria, we said there's a desire to go to equilibria. But if you think about it, it's a very important question is how actually are the equilibrium. What is the path to equilibrium? And this is described in particular by the PDEs of fluid dynamics, for instance, like where are they? The conservation laws of mass, momentum, and energy, and you need constitutive equations. And all this has to be compatible with the second law. So this is stuff I will not go deeper in. So Prigogine came up with this idea because he found a simple example where in a heat-conducting body he could show that the way to equilibrium, right? So you have a heat-conducting body and you say you have a rod with a temperature profile and then you wait until the temperature is equilibrated. And for his example, he found that this is actually the path where the entropy generation is maximum as compared to other ways you could go. This equilibration process that is prescribed by Fourier's law. But if you look at this more carefully, so in particular, I think he assumed particular dependency of the heat, or you had to either have a linearized system or you needed, I think he had a linearized system. If you take a nonlinear system, in order to have this principle at work, you would have, there's a paper I've seen, you would have to have a particular dependence of the heat conduction coefficient on temperature. And nature doesn't care about principles, nature does care about what happens, and it seems that there is not really anything that states this, that there is, that the system goes the fastest way to equilibrium that it can. What happens is, and maybe that is a way to look at it, that locally the system wants to go to an equilibrium, right? So you have a local cell and it interacts with what is all around it, and the cell itself wants to go to the equilibrium state based on whatever properties it has, but it has also to communicate with the neighbors. And that communication is something you have to account for. It's something that has to do with the interactions between the particles of the cells. It's nothing to do with the second law alone. So I've not seen anything that can tell you out of the second law. I mean, you have the second law, you can write the local second law, but I might even have it somewhere. But like here, but you will always end up with material parameters like heat conductivity, viscosity, diffusion coefficients. Those depend on the interaction, on the molecular interaction between particles in the matter, and not on your wish on a principle. So people talk about it once in a while. I've recently seen a talk about the steepest descent stuff, but really this is not mainstream stuff. Typically you have to look at finding a good local description and then you take it from there.
It's important for us to have some of the evaluation sheets back. I don't know if you received some, so please just put them on the desk here. And Henning will be around here for the whole of September, sitting upstairs on the third floor. Please go visit him in his office, have any questions about energy.
Or anything else, if you like.
And thanks for coming.
Thank you.